Professor Kumar Sharma is going to give a lecture on this, mostly on this, how we can do usage of the remanufacturing and how we can able to generate the path planning, how we can able to acquire the data for remanufacturing or repairing of parts using DED and all. He has done a lot of research work on these aspects and all. He has completed his bachelor's from IIT Dhanbad and doctoral and master's from the University of Science in 2015. After that, he has worked in disaster system for several years. Then he is moved to NIT Warangal. His major research work in aspects of the geometric modeling for the CAD and design optimization methods, and as well as the additive manufacturing and computational product designs and all. And he has published several papers, and also he has having 5 patents from the US as well as from the Germany and all. Welcome over.
Thank you, Dr. for introduction. Today, since I work mainly in the direction of computer design, so from the CAD perspective, how can we retrieve the damaged part in the form of digital model and then analyze about the amount of the material that we need to deposit, and then developing the path planning technique for DMD process. That will be the overview for today's lecture. So I'll start now. So we go through motivation. That is already you have been going through the GIAN program, so just will brief it out. Repair techniques, and then the way we repair, is it analogous or similar to 3D printing process? And the main steps for repair, one is geometric preparation. It means the damaged part, how we recover that damaged part. We need to get its 3D model. That is the geometric preparation. So it will involve certain steps. And then we'll go to the second main aspect. Okay, once you have 3D data of the part that you want to repair or recover, how to go for path planning, that will be a lot, how to define the deposition path for DMD process. These are the 2 aspects. Just to read this. So we know that the DMD process is mainly applicable for repairing hard to machine components, and it has been widely used for repair of turbine blades, molds and dies, cracks, or any thinning that we observe in the aerospace component. So you can repair that. The principle that it uses is localized controlled heating. So localized controlled heating provides it, makes it more effective in depositing the material. So this is the example that you may have already seen. Say there is a teeth profile, medical teeth profile, which is damaged. So through DMD process, how can we recover it? This. And it is being used after printing. Okay, this is the overview diagram. So for example, let us take an example of turbine blade. So say, as you see, there is I don't know if it is visible to everyone, backside. Say the trailing edge of a turbine blade has some crack defect. Leading edge can also have any defect like this. And there is a pressure side, there can be some damage, or suction side there can be any damage. So what we can do is, if we have the CAD data, that is, you can say in roughly, say you have a set of points, all the points on this turbine blade, and those points will be large set of points, so it can be millions. Then what you can do in the CAD system, there are, you can model this volume that you need to recover. You can fill it. Similarly here, you can fill it. Suction side, pressure side, you can fill those pieces. Right? The way you do the 3D model, you can use those functionality to do this. And then this is same as you have seen in the houses. If there is some crack, right? If there is some voids, protrusions, right? Or depressions are there. Some depressions are there. Then what you can do with the cement, right? You put it over it, plaster it, and get that. So this reason, which is to be kept here, will look like this. This is the volume that needs to be repaired. Now this repaired volume has to be deposited by DMD process. So there is an additional step. So here you can know what volume to be deposited. The next step is how this volume will be deposited will be dependent on. So now it is a 3D, like a 3D printing process. You need to spray the powder, and along with the laser you have to heat it. And just like your welding process, you will be recreating this volume. So that means what path you want to move this deposit material, and what are your deposition details. Deposition details is what is the feed rate, what is the volume that you will deposit at any point. So these are the rules. You can look at this figure to give you a complete picture of how a model can be repaired virtually. As you see, there is some void which represents a defect. This can be filled in this way in your CAD system, and then you can just remove and make it aligned with the faces. So this is the rough idea. Okay. We also know the DMD process or DD process. Necessarily, this is also a layer-wise application. So there is a need for slicing or toolpath planning. Slicing and then toolpath planning. There is a need, but there is a fundamental difference in the way this technique is used compared to the 3D printing. Here, since you can have change in the deposition rate, right? So you can have a small bead to the large bead within the layer. That is a possibility in DMD. Unlike in 3D printing, where layer thickness over a slice will keep it as almost the same. And toolpath planning. Now the distinction between 3D printing and DMD. If you see in DMD, you can deposit the path. Deposition path can look like a non-linear, non-planar. So, for example, I can deposit a paraboloid shape in the single run. So it is more like a 3D deposition. But if you see 3D printer, it is 2D deposition, 2.5D deposition. So constant width you will deposit at a time. So this is how the toolpath planning here will be very different from 3D printing. Here, as you are aware, since we are depositing a surface or depositing on the surface in 3D, so it might need the toolpath that is used by CNC machining. So in CNC machining, you have seen that when you go for subtractive process, you want to remove the material. For example, you want to fabricate a cylindrical surface. So the tool path will be over the cylindrical surface. So it is a cylindrical profile that you are developing. So it can be like a helical spiral path in 3D, right? Similarly, you have now this path is not in 2D, it is not on the plane, it is in 3D, right? So this is the distinguishing feature here. So your cool path can be in 3D, not necessarily in 2D. So these are the two distinguishing features. Now we'll go stepwise how to do this repair work. Okay. So first of all, as we have seen, you need to get the 3D model. So first of all, you all know about the scanning of the damaged part. So are you all aware of it? Okay. So I just walk through it. So the main philosophy is you need to collect points on the damaged components. How do we do that? So this is about, there is some point on 3D model that is x, y, z coordinate with respect to some global coordinates. You want to get that x, y, z. And this is not about one point. You have to get whatever thousand of points or lakhs of points on the surface. The more number of points you get on the surface, the accuracy of the model that you capture is good. The accuracy will be good. Okay. So we use these three technologies: laser scanners. These are the examples that these devices are from these companies. Structured light scanner, which works essentially the similar principle, only the light source is little structured. It can have some masking or some kind of pattern that helps us to operate over smaller resolutions. So more or less first and second have the same philosophy. The third one is photogrammetry, where with photos you can collect photos, take the 2D data, that is the 2D image. But when you take multiple of 2D images, can we create the 3D model? So it works on that principle. So we'll focus mainly on laser scanners. So the principle of laser scanner is same as, for example, you have a scanning device which works from the distance. You want to measure x, y, z coordinates from distance. So a simpler example you can see, suppose you have a hill or some rooftop, right, where you cannot reach, and still you want to measure the height of that hill or roof. How will you do that? So this is simple trigonometric problem. We don't want to, do any point cloud detection or anything. All we do is we have some sensor that measures the angle. So suppose you have a sensing device, this throws the light here, measures the angle, at what angle I am. Now I move a distance L. Once I know alpha, I move a distance L on the ground, and again measure the inclination angle beta. So once I know alpha and beta and L, I can calculate the height, right? You can use the triangular rules. Right? Similarly here, the principle is essentially the same. It is called triangulation technique to measure. So here there is an ammeter that goes to the point, to the object, and then it is received here. So we can measure this angle, alpha and beta, right? And the separation between ammeter and receiver that is available within the scanning device. So by measuring these angles and B, we can calculate the position of point B related to the ammeter. So hence you can get the x, y, z coordinate of points. And these scanning devices can scan and get thousands of points in this. So this is the principle. Internally, you can look, this is for your reference, you can see, okay, this is basically how it calculates x, y, z. This is for your reference. I'll share this quickly. So this is about collecting points. So you know this collection of the points is not accurate because each device has its own accuracy. So in case of laser triangulation, this is called laser triangulation technique. You can get this accuracy of 0.01 mm at best. And resolution is important. Sometimes if you have thin features, you know whether we can measure it or not with this device. So that is where it is important to know how much thin objects can be measured. So this is where we focus. While others like structured light, almost the same accuracy, but you can have resolution of 0.05 mm. So this is also widely used. And then there are other metrology techniques, time of flight technique, right? So this is basically used by civil engineers. You may have seen civil engineers, making the road map or understanding the, collecting the data about the terrain, right? Or this satellite collecting the terrain information. They all use time of flight principle, where the emitter will send the light, and then the reflected one is measured by using the time of flight. Okay. So this is a bit different principle compared to the laser triangulation. Then industrial CT scanning. So you know that X-ray data, that X-ray, because its wavelength is low, this can measure at micro resolution the internal structure. So not only on the surface but also the internal details of, as we have seen in case of human body, you can also measure the internal details. This is what we will focus on. Now, how the scan data looks like. So there are various file formats. Will not go through it, but I will just mention some of the file formats for. I just write it down. Once, I think, are you aware of it? So how the point clouds, point data is stored. Once you collect the points through the scan data, how it is stored? Do you know that? Okay, I'll tell you a simple idea. So this first step is collect the points. After scanning, each software can have their own format, but the one that is the simplest one is this file format, which you will remember .xyz. Okay, so this is the file. Why it is important? Because whatever you see in 3D is actually stored somewhere. It is in the file. And how it is stored? It is just giving you x coordinate, y coordinate, say x1, y1, z1, x2, y2, z2, and so on. Right? If thousands of points are there, you will see this table of x, y, z coordinates. It can be with normal and without normal. What is the meaning of normal? At any point, you can get the normal to the surface. Okay. So x, y, z format comes with and without normal. So normal, if there is a normal, then you will get another detail. So normal is a vector. So there will be x component, y component, and z component. So n1x, n1y, n1z. Similarly, n2x, n2y, n2z, and so on. So this will be the common format. You can always look for this format after scanning. Any software will give you. So what you can do is you can go to this link graphics.stanford.edu 3D scan that. There you can see lot of models. So whether it is a statue of Michelangelo, so big statues, they have scanned, stored in certain files format, and they will the repository is available. You will find other file formats also. file formats are OBJ. So star means the name of the file. OBJ and VRML. Then you know STL file format. So it may or may not contain the triangles, it may contain the points. So these all can be available, which can contain the points. Okay. Any questions here? So this was the first step. Collect points on the damaged component. So we understood the principle. Any question you have? And once you scan with this accuracy, you can store in certain files.
Scanner type is designed by
Yes.
nature of defect or the nature size of defects or different materials. What decides the scanner type?
Yeah, here as you can see the accuracy or the resolution. But mainly we are focusing on laser scanning to get the details. Again, mechanical component, this is what we are using. But you can have, if you know, this is non-contact devices. But you can use CMM. But again, with CMM, you can measure only few points. Right? So it depends. Now, this is the call you need to take when you want to reconstruct. You need to see the damage, nature of the damage, right? And you have to retrieve the point. But there in photogrammetry also, there are a lot of techniques. But we focus on non-contact type, right?
So only triangular packets made in this process. Packets that made nothing. Only triangular format or any other.
So usually when we have point cloud, right, the best way to fit a surface is by triangulation. So you know that 3 points can be connected by a triangle. Right? If you connect it by quadrilateral, say 4 points you connect by the quadrilateral, you lose some accuracy. So mostly all these files will contain the triangles. But the organization of points and the triangles, how they are stored, structure may be different. The purpose these are made are different. For example, if you see this HTL file was created for this our stereolithography purpose, right? This OBJ and VRML was created by our multimedia graphics people. Okay. The purpose was different, so that is where, but essentially they store triangulation kind of technique, triangulation kind of data. But these formats also allow to store points. It depends, right? That we can check if they are storing the points. But if they are storing the point, it will be similar. XYZ format is the one. There is another file format that store point, that is .asc. So these are mainly used. Yeah. Yeah. Not, in the 3D, in the sense your thickness of the layer is changing, right? So you can deposit at different rate over one layer. So then that way, what happens is, if you take, I take this 2D example, the way you can deposit is, say I can have one layer like this. This is one layer. Then when I build on the top, I can go with another layer like this.
Variation of thickness we can.
Yeah. And then last layer can be like this. Now, comparatively to your 3D printing, will go like this. As a result, what happens? You need less number of layers here. It can be fast, right? Compared to this. Second, the accuracy again will be better, because here you will have like this staircase effect. Yeah, overlap that will come. Overlap or underlap. So you have to see that part. Right. So these are the rules.
If we are creating everything, we get overlapping terms. XYZ format file, whatever that overlapping terms, it will not consider overlapping.
Okay. No, this XYZ format, like we have not come here. XYZ format is about scanning the damaged part, getting the 3D data. Okay, it will be clear next slide. Okay, now the next question is, we have point cloud. So you see some hand here. Okay, this hand is nothing but point cloud. Okay. This hand is nothing but point cloud. So someone with the scanning, we can just scan our palms. Right? This is not the solid model. Solid means it is no connectivity is there. It is not the surface. Can you distinguish between surface and point cloud? So surface is continuity. There is you can move on the surface. Point cloud, there is no path. Right?
Planes and lines.
Yeah, it is just black dots, that's all. This is the surface which is constructed. It is like skimming over the point. Now the question is, how do we reconstruct the 3D point cloud from the how do we reconstruct the surface from the point cloud? Okay. So I'll give you a basic idea. So let us say, there is something, some object in 2D. Take it as a circle. Right? Take a circle. So suppose there is an object which is like a ring, and you have scanned the circle, this ring, right? So what you get is a lot of points along the ring. You can get the idea, this is some circle, right? So you can use mathematical tools to fit the circle, right? So you can recover a circle, right? This is one way. You can fit and get it, right? Now, there is another way. What you can do, rather than fitting so many points into a curve, may result into problems. Okay, so the problems are mainly you may not get you may get some deviations. Okay. So let us think of it in another way. This circle, the ring, the object which we are scanning, has some center here, right? So similarly, from point cloud, if I can get where is its center, right? Where is its center? So now, when you have the scan data, you have point cloud. Can we get the center? And if we know the radius, then all we need to do is you can recreate the or reconstruct the circle or the ring, isn't it? So this idea is used here. So what does that mean? So when you look into this hand, right? I'll show you another simpler example, and then you can get this idea. So let us see. This is like your circle, right? There is an object. You see the boundary of the curve, right? This is the actual 3D model. Now we'll use the same idea. If you take a disc, if you take a disc, what you can do, just like this ring, you can take this object. It may not be looking the same, but you have this object. What you do is fill it with lot of circles. My circles may not look good, but good to capture the idea. So you fill it with This is mathematical. You fill it with maximal circles. It means the circle which just touches the boundary. Okay, the circle will just touch the boundary. Now you trace the center of the circles. It will give you this figure. Okay, you try it out on your own.
That path.
Yeah, that path, internal one. Okay, now we'll use the same idea. Now, what are we saying here is from point cloud. This is the original model, right? We have the boundary. Now, the point cloud for this object is this, which you see in the detailed points, right? So, can we get this center of circles in some way, right? And then we just take those circles and do the union of those circles, right? So, if I take these set of circles, right, and then I do the union of so many circles, I get the, if the number of circles is quite high, you will get the exact boundary. Okay, so this is what is being done. So this method of getting the centers, this diagram, can anyone tell what is this diagram? You see certain edges. Anybody knows this? These set of edges. So this is a point. There is one edge. What does it look like? It's called Voronoi diagram. I think you may have heard of Voronoi diagram. What is Voronoi diagram? Actually, it is the set of points which are equidistant from 2 points. So this is called Voronoi diagram, and this point, this particular point that you see where the circle center is there, it is called Voronoi pole. So this Voronoi pole acts as the center of the circle. Okay, so you can look about more details in this paper. Okay. So this Voronoi diagram is the methodology used to get the possible centers. And then once we get these Voronoi poles, in this figure if you see all these vertices that you see 1, 2, 3, 4, 5, 6, 7, we just generate a circle. Now look at the circle. How to get the circle? You take the center and the maximum radius you will take such that it connects to the outer points. So 1, 2 and 3. To inscribe a unique circle you need at least 3 points. So you will take a circle that connects the 3 closest points on the boundary. And then you take the union of it and you recover the whole 3D model. This algorithm is called power crust algorithm. Okay. So power crust means what? Crust, you know, it's like a surface, right? Power. Now you are using the circle, right? The maximal circle. The power of this circle is till boundary, till crust. Not beyond, not below. Okay. So this is to give you a rough idea. Okay. I believe if you understand this notion, you know, this technique is generalization of identifying the centers of maximal disk from the point cloud and then taking the union of the ball to get the outer surface. Okay. So this is the reconstruction algorithm. Now let me go to the previous diagram for this. Okay. In this figure, what you see is actually this is also locus of the center of the maximal circles. In this case, it is a 3D sphere. So that is why we call the word balls. In 2D, maximal inscribed circle. In 3D, like a palm, it will be like my bones. The bones or the center of the bone will form the center of the disc or the ball. So in 3D, it is a sphere. So when you trace all the centers of the sphere, it will look like this. Okay. So what we do, the principle is take the point cloud, generate Voronoi diagram, take the maximal ball centered at the Voronoi pole such that it passes through the 3 points, at least 3 points in case of circle in 2D, and sphere 4 points are enough. How many points are required to define the unique sphere? Okay, 4 points, right? And then once you get all the spheres, right, you do the union, right? When you do the union, what happens? You know about union. Union will Boolean union operation will combine all these spheres, right? And it will make the whole solid. Right? So union is just like Lego. You know, you combine everything and get the full building. That is the name. So you get the 3D. So this is the main idea of reconstruction. Any question here? This was the second step. So this will construct the 3D model. Okay. There are many more methods, but this is the best. It gives you watertight solid. Watertight solid means a valid solid. Okay. Is it clear? Yeah.
Reconstructing in 3D, but what about in the practical? How
Yes.
the arm will be deposited? We move in only linear direction.
Which one?
Deposition.
But that is deposition process. Right now we are talking about you have a scanner, you have scanned the object, you get the points. Now from the points you need to get the surface. So that is what we have done. Surface, the outer skin you will get, continuous outer skin. Now third step is, now you have reconstructed the damaged part and you have a digital data in certain file format.
So,
Yeah.
the object is a larger one.
Yes.
In that case, we will have to scan the file in different number of times.
Number of times, yeah. Actually, people are able to scan with ships also they are scanning. Power plant also they are scanning nowadays. So number of scanning means it is like you have to move the scanner. The scanner can move.
With the height, we can say.
Yes.
It is just a 10 mm.
Yeah.
1 meter. In that case, the scanner can take only 100 mm for a single step. So after that, we will go for second step. So
Yeah.
do we need to give any overlapping between these two?
You can give, the softwares will handle. If there is a overlap, there will be duplications, it will remove.
Those
Yeah. Yeah. So there are a lot of scanners nowadays. Scanning the smaller one to bigger range can be done easily. So many are equipped with robotic arm also, so that you can scan. Right. Sometimes some scanners are like scanner remains fixed, and you have a turntable. The object will be kept, the table will move, and it will scan. We can scan ourselves also, right? You may have seen a lot of videos. Right? So those are the scanners that are used. So lidar scanner, mainly it has less accuracy, but it is used by this autonomous vehicle navigation. So as it is moving, it will map the geography, right, surroundings. Right? The accuracy is much lower, but those are another example, lidar based. So now from point cloud we got this solid model. Now this is the solid which you can save in the standard CAD format. The standard CAD formats are step. These are the formats that are used, that can be used across the softwares, IGS. But since actually this these are mainly after union of ball, right? The surface that we get, best is it will be collection of triangles only, because that is the best way, most accurate way to save it for the point clouds. So you may get all the formats that store the triangles, STL, OBJ, and so now you have the 3D model of the damaged part. Now what to do? You may have the CAD model of the component. Say turbine blade is there. You will have the CAD model also. And now you got the 3D model of the part which is damaged. Now what you will do? You have to compare and see what is the damage. How much is the damage? We want to recreate that damage, right? So you know, na? For example, you have, usually a manufactured component will have some undulations, right? It will be like this. Some tolerance. It may not be completely flat, right? It may not be completely flat. It may have some undulations. And CAD model looks like this, perfectly flat, right? So this is your designed CAD model, and this is your manufactured. If you want to know how much is the deviation, right? What you will do? You will overlap both, measure the difference. What exactly you will do? You will take maybe lot of points here, right, on this space, and same number of points here, right, such that this point, say IL point here, should correspond to IL point here, right? What you will do? You will measure you will overlap it, right? So maybe you will overlap like this. This is the CAD model, this is the manufacturing model. You will calculate this deviation, the distance between 2 points, the manufactured and the design, right? Take its magnitude. Similarly, you will do it for others, right? You will calculate, say, I am assuming any point P is here, PI, and any point here is QI. So Pi minus Qi, you will take the difference, that is this distance, right? This is Pi, this is Qi, this distance is Pi minus Qi, right? Then you will sum it up. I is equals to 1 to many points that you, as many points as you have sampled, right? Whether on this and whether on this, right? So we will sum it up, that will be your error, right? This is one way to measure the error. You can calculate standard deviation also. So you can take the mean error. What is the mean error? So you can just divide it by number of points. This is the mean error. You can calculate standard deviation error. So this is the way you have been comparing the design part with the manufactured part. Same goes here. But there is a problem even here. What you need to do? There is something like you have a CAD model in the SolidWorks or CATIA or anywhere. It is at certain global coordinate system, right? It is defined at certain global coordinate system. And the manufactured part is also defined in another coordinate system, right? So we have to overlap them. How do we overlap them? So that is the step 3. That is called registration. Registration of the reconstructed solid with the CAD model. So here what is shown is based on the coordinate system, this one, the blue one is the CAD model, and this one is the scan model, right? Both using different coordinate system. When you bring it into the system, then both will not be aligned. Now you have to align them. How do you align them? Any idea? So you have to align, and this, after aligning, you will get overlap. So this overlap, bunny contains both actually. You see both are overlapping. So these are the steps. So how do we align it? So let me show you. There are various techniques. It depends on the complexity of the part. Okay. So initial alignment. you know that if there is a cube, right? Cube manufactured, cube design. You can take the corner of the cube and try to align the corner, right? So maybe you can take the vertices, right? 3 lines, and try to align the 3 lines to another one. Right? So this is the simplest thing. Manual alignment. Or you can say landmark or the feature based. Say there is a hole, right? You know this object has a hole, that object is a hole. Let me align the hole to hole, then rest of the object gets aligned, right? So these are like 2 techniques widely used: landmark or the feature based. Okay, I show you an example which will be clear to you. So there is a link provided. More details about mathematics of it, you can go through this tutorial. This is so there is a YouTube video. There is a software called Cloud Compare. You can just it's an open source. You can try that software. And this is an example of alignment. So this Cloud Compare is the software which is available. Now let us say there are 2. So one is the CAD. Right now both are point cloud, but it need not to be, but can be triangulated one also. So here it takes few points. So these are the points on the periphery of the circle. Same points can be marked on the periphery of another point cloud. And then when you align, right, what it does, it calculates the transformation that is required to align the point cloud with the CAD model. What are those transformations? There are 2 transformations only: rotation and translation. So there is a lecture available. So you see what it does here. So it is the aligned part, right? After selecting those 2 points, it has aligned. So what it has calculated? Actually, in this matrix, you can see it's not visible, but I will tell you. Actually, it calculates the rotation. This is the rotation component, okay, and this is the translation component. So this point cloud data, how much you have to translate and how much you have to rotate, right, to fit in the CAD model. So these are the 2 things it calculates. So this is called initial alignment. The initial alignment, in some cases, right, in case of these kind of objects that you saw with circles and the lines, it will align very well in the initial alignment. But if you take the example of bunny or certain other complex shapes, it may have some deviations. So how to further reduce that deviation? So we apply another technique that is called fine alignment, and the technique is called iterative closest point. So what does it do? So for example, if you take 2 lines, 2 curves, these are the blue one, just assume it is your CAD model, and the red one is coming from point cloud. Okay, so now both in the initial alignment have come close to each other almost, but they have not overlapped because of the complexity on the curve. Then we have to apply this technique, iterative closest point, and we get this, all the points get overlapped. Okay, so what does it do? Internally it runs an objective function. What is the objective here? So you can get the idea on its own. As you need for research, you can explore, and also there are already MATLAB code available for all this, but you should know what technique to use. Right? You can go deeper into it. Right now we'll get the idea. So let us take any point here. So I have this habit of going to the board and saying. So let us take one point. One point is here, and another point corresponding is here, right? So we calculate the error, right? So let me show you. Let me take a point Q, or let me take the point P. P is the point on the point cloud, right? Then what we do, corresponding to that point on the CAD model, how to get that point, the corresponding point of the CAD model, what we do is calculate the shortest distance between this point and this curve. Okay, so that distance will give you the corresponding point. So I will just try to make it. This looks like this. This is like this. So what you do, you take the closest point. So this equation is available with us, and this is the point P. Calculate the closest distance. How to calculate the closest distance between two curves? There is a small mathematics, you can do that. Okay. So what happens when it is closest? So actually this vector will be normal to the tangent vector to the curve. That will help you to get this point. So once you get this PI point is closest to this point, this is the corresponding point, right? You can take the magnitude of it, right? And likewise, in the point cloud there will be a lot of points. You can sum it up, right? And calculate the error. Now your goal is to minimize this error. Okay? So let's go to the next. What we do, we solve it as an optimization problem. So the closest point you can get Pi minus Q, as we have seen. Our goal is this, once it overlaps, right, this point cloud and this curve, the distance will be 0, this error will become 0. So our goal is to make it 0. How to do that? So our goal is to make it 0. So for that, what we do is, we need to move this curve. How can we move this curve? We have to move it in certain way. Either we translate or rotate, right? So you can take this example. Suppose in this case, I cannot take the example of the palm, but if there is another person, right? He has the right hand palm, and I have my right hand palm. Both are spatially oriented differently. So to make it overlap, what I have to do, I can either translate means moving in one direction, or rotate. So we need to calculate these matrices. So what we do here is, we formulate a problem like this. So R into Pi, R is rotation. How much rotation I should make to this point cloud, right? Pi, and how much I translate. This rotation and translation will give you the new position of the point cloud data. Difference with point Qi. Whole square or magnitude. Whole square is the best, because then you can solve it. If you take magnitude, you have to worry about a lot of things. So this will be subjected to, this is R is rotation matrix. R transpose R is identity, and determinant of rotation matrix is always 1. It will give you, at each time step, a new rotation matrix and the translation matrix, right? And then what we do, we will transform the point cloud by this rotation matrix and translation matrix. You get a new set of point cloud data. Then again you apply this technique to calculate the new rotation and transformation based on error minimization. So what will happen, every time your right hand palm will translate and rotate and try to come closer to somebody's palm, right? Every time it will calculate that, and finally it will register. This is called time registration. So it needs some, the basic idea is about how much I should translate, how much I should rotate at each time step. Okay, does it make sense? Once you do it, you will know. Okay, so this is called iterative closest point. You can check. There is a good tutorial available, right? And it will help you when you use crowd compare or other software. You know what exactly you need to do. So with these two steps, what you have achieved, you are getting the overlap between CAD model and the scanned model, scanned data. Okay. Now what we need to do, once you have overlapped the defective part with the CAD model, all you need to do is calculate the difference. What is that difference, right? And that will be the volume that you need to recreate or reproduce, right, for the defective part. Is that okay? So this much work we did, right, to get this. What is the remaining volume that we need to reproduce? Okay. So now it is clear. We can do A minus B, say A minus B operation. That is the Boolean operation. So original CAD model is stored as A. The 3D model of the defective component is B. So A minus B will give you the repair volume. This is the repair volume or recover CAD model. So once you have a CAD model, then you can use DAD 3D printing any technique to reproduce it. Okay. So now the next step is, sometimes we may not have the CAD model, isn't it? You may not have the CAD model. That is the case with lot of our turbine blades, motors which are old. And also we lose the CAD models. Right? Sometimes the manufacturer from where we have taken, we may not get the original CAD model. We may have some drawings.
Sir, excuse me, any other compatible software for doing this translation?
No, CAD software you can do. For registration, Cloud Compare you can do. Cloud Compare, then this to my mind right now Cloud Compare comes, which is open source and you can use it. Mesh Lab is another software.
Okay, thank you.
If time permits, sometimes I will show you a software also. Today may not be possible. So let us go to the next step. Now, if the original CAD model is not there, then what to do? We have half an hour. So this is an example of a ship hull. Okay. So these are the two views. So this is the damaged part of the ship hull. Okay. Now you don't have the CAD model. I made it in CAD model. It is to teach, but you can assume this is the real data. Okay, real damaged part. Okay. So how will you patch it up? How will you patch it up? So this is a surface, right? This is a surface. How will you create the patch? And then how will you define the deposition path for DMP?
The translation mission.
Yeah.
In the translation you said first you will create one layer scan, second layer scan, then two layer scan. This is the thickness system. So that then you will overlap again points. You get a thickness into three dimensions.
Okay, we'll just see here. We don't need to think about registration process, right? So this is a simple problem. If you are given some hints here, right? The boundary curves you see in the blue or in green, there are certain boundary curves. So I will take an example. Suppose one boundary is like this in the 3D, right? Another boundary is like this, another boundary is like this, another boundary is this, right? So all you need to do is create a surface using those boundaries. Right? Create a surface using those boundaries. Umbrella, have you seen that? Umbrella, the boundary remains same and you can get different surfaces. Right? So it's like this now. So you are given the boundary. This boundary is not in 2D, it is in 3D. Right? So how to get this surface equation? So I don't know if you have studied about surface representation in CAD. So you can take an example of simple, as an idea of interpolation. So to get the surface from the boundary curve, all you need to do is find the surface which interpolates the boundary curves. This is same as if you have set of points, find the curve that interpolates these set of points, right? So we are saying the same thing. If you have lot of points in 3D, find the surface that interpolates these points, will give you a surface. Okay, so interpolating surface. The idea is the same. It is interpolation surface. So now, concept of how to recreate this surface. Okay, you take the main idea, it's about interpolation, nothing else. How to do that interpolation? So let us understand the concept behind it. Let us assume this is a surface, right? The boundary curve we can define parametrically. Say this is a P of u comma 0. It can have some equation, say v0 into u plus v1 into u square, right? That is a quadratic curve. Similarly, another curve that is P of u comma 1. So these are function of u parameter, and this is another curve P0W. So what is the equation? If you take quadratic, say C0W plus C1W square. Similarly here W. So why there are two parameters u and W? Actually it is called parametric surface, and what it does is you have u and W, and this equation maps any point in this parametric space. It will have mainly the value u will be from 0 to 1, W will be 0 to 1. Any point here will be mapped on the 3D surface. So here it is 2D, it maps to 3D. So it is x, y, z, and here it is, its coordinate is some u, I, W, G. So remember, the problem is we are given the boundary curves, not the surface. How to get the surface? So one of the things that we can do is, if you know, as I told you, it's about interpolation. So this one, P of u0 and P of u1, these are the two curves. Can you create a surface passing through those two curves? Right? How to do that? You can use another parameter 1 minus W into P of u0 plus W. Okay? So what does that mean? So this is P of u0, this is P of u1. when you use W parameter like this, interpolating two curves, it will create this surface. Does that make sense?
Yeah.
I have the MATLAB code, I share, you execute it and you will understand. So this is one surface which respects these two boundary curves. Now this is another surface. This is P of 0W, right? This boundary curve, right? This boundary curve is P0W, this boundary curve is P1W. If I interpolate using another variable, not W, I have to use another variable. Remember, U will be in this direction, right? So actually, this curve, this section is mapped to this section. This section is mapped to this section. Okay? And similarly, this section, which is along W, is mapped to this side. And this section is mapped to this section. Okay. So now, I can create this surface H2. Now, original surface, what is the original surface? Original surface should, respect four boundaries. Right? The four boundaries were this and this and this. In this surface, it respects two boundary curves. Here it respects other two boundary curves, right? So can we say, if we want to create a surface which respect all the four boundary curves, can we say this will be S1 plus S2? So this is S1 and this is S2. So to make it work for all the four boundary curves, can we say S1 plus S2? Okay. So you will find that's not true because it will not, satisfy all the four boundary conditions. So there is something to be subtracted. So there is something which needs to be subtracted to get the surface which respects all the four boundary curves. What needs to be subtracted is S3. Okay, what is S3? So what we'll see that this S3 is actually using, it's an interpolation of four corner points. Okay, this will be the equation. P00 represents A. Okay, U is 0. So P10 represents another end. So where is P00? This is P00, this is P10, this is P11, this is P01. Interpolation of four corner points. We need to subtract and then we'll get the original surface. Okay. So this is the surface that respects all the four boundary curves. This is called Coon's patch. Okay. So what we did, for the case of boat, if you see some damage, all you need to do is look at the boundaries, four boundaries, right, on that damaged part, recreate the surface using this equation. Now when you have this equation, it means you have the CAD model actually. This is the surface equation. Now can we create a deposition path using this surface? We can. So what we can do is, so these are few examples. Say if your boundary curve is like this, 1, 2, 3, 4, right? So this is the surface. So this is the S1 plus S2, S3, and minus S3. S1 plus S2 minus S3. Okay, these are few examples. You can visit this mathcurve.com. Now this is for you to practice, but you can go home and try defining a surface, use that same equation. So there are four curves. Till now we were just telling P of U0, but we are not saying what is it. So actually it is U comma 0 comma sine of pi U. It is a sinusoidal curve. P of 0W, 0W sine of pi W, sinusoidal curve. Similarly for U1 and these are the four boundary curves given in terms of sine and cosine, and you have to find out the solution, the surface that matches it. This is the answer. You can write a MATLAB code and see that. Just to close, sometimes it may not be a surface, it may be a surface with thickness. So you can, if there is a surface, you can extrude it. If there are multiple surfaces, right, if the part is thick, so what you can do, again you can use the idea. So for example, one surface at the bottom looks like this, other looks like this. So you can also create a solid by interpolating multiple surfaces. In this case, just linear interpolation is done and solid is created. So that can be the possibility if the surface is thick. So I'll go to the next thing here and show you how to, there is something. I'll just try to show you how to create this surface and how to create the deposition part. Okay, here I have a MATLAB code. I'll share you. What we have done is we have just defined the boundary curves like this. Okay. Let's see if it is done. So the way to plot is here you have some if you know how to plot a surface, you can do this. Okay, there is a mesh grid function that can help you to create a surface. Okay, I cannot go in detail, but mesh grid, if you understand, you will know how to create a surface. So it will run. It might take a while. So right now I just take. Actually, it will create the surface as well as the deposition part, which is very close to this surface equation. Okay, so this is the surface. Actually, it is not the sine pi one, it is different one. I plot that also. So here it has the sinusoidal curve along u direction, right? Here and here it is sinusoidal, but the other direction it is quadratic curve. Okay. So this is the surface. Now we know this is direction for parameter u, this is the direction for parameter w. If I keep w as fixed and change u, right, you will get a curve. So that is what is being shown in this figure. So at certain separation, you will get first boundary curve. Now you keep w as fixed. Here I think 0.2 is w, and you substitute it to the s of u comma w. You will get a curve. There another curve, another curve. So these are actually can be served as a deposition path. These are called isoparametric paths. Okay, why iso? Same parameter, right? W is fixed. So whenever in a surface which is a function of u and w, you keep one parameter as fixed, the surface will reduce to the curve. You can change the resolution. Suppose you want to deposit at closed spaces, you can have many more isoparametric curves. So this is one way. Does it make sense? Okay. You can rebuild this surface by depositing in this way by using isoparametric curve along u. You can go in another direction also. You can deposit in this way also. That is, this is the boundary curve along w for u equals to 0. So you can get the first boundary curve. Then you can get the second. Then you can get third. All the way till here. Now you can analyze as part of process planning which direction is the best. You can also choose combination of certain direction, right? You can take care of it by, as I told you, the mathematics you can understand, there is nothing much, but you can choose any other direction to create a surface. So we showed you, this is a U, right? And this is W. So you can deposit. If I go along this, you are keeping W as fixed, right? You can deposit like this. Now, if you keep U as fixed in this direction, right? So you can deposit like this. Or I can also choose another direction, that is, say, I can take another color. So I can choose another directions, right? And in this case, your curve will be generated in this way. Okay? What it will be? Can you get these lines? Set of lines in U and W. It will be combination of U and W, right? Combination of two vectors. Right? So here, if you say it as another parameter R is lambda1 of U plus lambda2 of W, right? You may have something. Lambda3. If lambda3 is 0, it passes through origin. Otherwise, it will be just lambda3 will be spacing between them. Lambda1, lambda2, lambda3 can be lambda1, lambda2 will tell you the direction. Okay? If it is 45 degree, 1 by 2 to 1 by 2 to something like that. So this is the deposition path. Now another point here is, look at the deposition path, the arrow. Right now I have used this direction. So it goes from here to here. And then the tool has to come back to again here. And then again go here. Then again come here. This is unidirectional deposition. Right? Which is inefficient because there is a redundant movement of the tool. You can go for, okay, I start from here and then go to here, then come back here, then again go here, come back here, then again go there, come back here. The continuous path. Right? So you can have two-way catching. So just run it again. Maybe this time I will run for the example practice problem that I have shown, and I will also increase the number of curves. So what they are most So now we want it to be continuous, so back and forth, just like. So now you see different surface. The example that I showed you in the PPT, where all the four boundary curves are sine or cosine. Okay, this is the 3D surface which you want to recreate. Right, this is a 3D surface. It might have been the top of certain object is gone and you want to regenerate it. And these are the deposition paths. So if you move along direction, it will look like this. So now in this case, I don't know if it has done its job. Okay. It is not continuous right now, it is not showing continuous, it is still showing in the, for some of them it is showing the, okay, actually I need to correct, there is a bug in the code. Actually here for 2 it shows in same direction and for other 2 it shows in the opposite direction. There is a bug in the code, I need to correct it. Actually it should go straight and then opposite, then straight, then opposite. It should move like this. That is all doable. You can modify this code. So I think this is all. This is about the deposition, and I think after that from this program you may have a lot of details about how to go with deposition. From reconstructed model, this is where we should end and carry the path deposition. Now how much deposition has to happen, what should be the speed, all that you all are aware. Any questions we can take?
The complete findings that we are focusing on is on scan time data, not on real time data.
Scan data is the real data. So what happens is the 3D model, the actual part which is damaged, right? We need to get the data points, the XYZ coordinate. We use the scanner, laser scanner. This gives you XYZ coordinate. So it is the real data. Okay, here I may not have taken the real data because I don't have. So I try to explain the concept using certain examples.
Give an example. Suppose we are making turbine there. So after we have some discussion on the
Yes.
surface. So we took a scan model, we scanned it, and we don't have the CAD model.
Yes.
So we are creating this.
Then you have to recreate.
Yes.
Yeah.
In the meantime, while we do these analysis, there is a chance of the oxidation may take place and the surface of the real time will be changing.
Will be changing. Then we need to get if you want to work with that, you again get the fresh data.
If in that case, if it is an emergency or urgency kind, we need to devolve it. So then how do we track this in real time?
The only way it is completely dependent on whatever you get from the scan. So I don't have from this perspective your answer. There is no solution from this kind of methodology. There is no solution for that. Yeah, but maybe can answer better. Right?
I have spoken I usually in a computer machine and I want to create the frame. Means the project to have 4 we have external and 14 will be again use the PA not PAC. How can I differentiate that?
So 2 materials it is using.
Yes. How can I differentiate that?
So there is something like one is the outer boundary you get here. Yes, the outer boundary of the tube that you can get here. Right? Now what you do is the internal boundary of where is that other material, the coating starts. That boundary will not be possible here because it takes the surface. That is the limitation. That is, scanning devices can give you the surface details, not the internal details. So you may, if you have based on your knowledge, where is the how far distance your coating starts. Because you have the outer boundary information. Where the coating starts, if you have an idea, you can create that.
So by reverse engineering we can find out the internal structure.
Internals. That is what I don't know if there is something. At least scanning devices takes the surface, but X-ray is one. But I don't know how well it can get. So X-ray kind of these techniques, non-destructive techniques, are used in composites to get the internal details. But in your case, if you have the idea from the original model, right, from the drawing, that how far is the coating surface, since you have already the boundary information, you can know that. So, given a CAD model, it is all about splitting the CAD model into two regions, one for one material and another model, that you can do. Then you have to think about the fabrication part. I don't know how it will be, so that will be another challenge.
So actually, this surface creation, this S1 plus S2 minus S3, it is to get that final S.
Final surface, which will interpolate all the four boundaries.
Yeah, which is yes. That means
yes.
So it is a, in my understanding, is it a kind of interpolation scheme?
It is an interpolation scheme.
S1 plus S2 minus S3. It's
S3. If you see S1
interpolation scheme you are using for generating this surface.
Surface, recreating the surface, which respects the, because you don't have surface information.
Yes.
You have only four boundaries in case of
someday we have to extrapolate it.
Yes.
So S1, S2, S3, it's extrapolating it based on that one and another.
Yes. Yes. In fact, what can happen? Here you have four boundaries. But what might happen in different situations? So, for example, four boundaries may not come like this in a rectangular patch.
Exactly.
There is a corner, right? So it may come like this. In case of Shikha, you are seeing, right? There is one boundary and then say something like this. Right? There we need to make, okay, this is one. Because you have the points, you can define the curve in parameter u or v or w. You can subdivide this entire curve into four patches. This will have one equation. This will have another equation. This will have another. So like that you can. This is one case. Another possibility is you can take bigger patch like this, right, on the hull, right? The undamaged part also you can take. Now, what you can do, you can create a surface. You can create a surface, and then the actual damage is in this region. Say, you can query that. The actual damage is in this surface. So what you do, you have an equation as of UW, but U of W is like this. So this is extrapolation, but okay, let me the actual damage region is in this zone, which looks like this, right? So all I need to do is I can get all the 1,000 of points here. I just substitute U and W in this region to this equation of S of U and W. I'll get everything.
It is almost like the IGA part what we use is being brought here.
What do you call this?
The method we use in the interpolation schemes we use in the isogeometric analysis.
Okay, in isogeometric analysis,
What is the basic difference between
B-spline NURBS based technique? NURBS is another representation, but it uses the two parameters, like parametric surface. So it is another technique. The parametric representation is, so that is what here. In
This
fact,
is something really new, and I see that I didn't see anywhere this algorithm. It seems like your own algorithm.
So I think this one I created last night thinking about. So this code I wrote last night.
That is why I have this question that you might have worked in that. I came to know that you are working in IGA. And do you feel that any difference between that the NURBS interpolation based scheme and this interpolation scheme, which is effectively making that surface?
Yes. Here, why we use NURBS is especially for mechanical engineering. It is not dependent on the degree, because we can fabricate something like third degree curve, right, at motion. That was a preference. So as you increase the control points, right, as you increase the number of control points, your degree can remain limited to quadratic or cubic, because we have fabrication issues. That's where splines were appreciated. Right? Because if you take any polynomial equation, right? If you have more data points, the degree of the curve will increase, right? But that's not the case in case of spline. That was the beauty of splines. And then in this case, the question that sir is asking is, can we have? So this is more generic. If you look at this equation, this is okay. S1, S2, and S3. Now S1 is P of U0, P of U1. It is a parametric curve. It can be Hermite curve, it can be Bezier curve, it can be B-spline curve, it can be any polynomial of any degree. So it is not dependent on the nature of curve. You can have anything. I have kept sinusoidal curves. Right? It can be anything.
Even it can be anything. This Watts-Crest based schemes also for polygons.
Radial basis functions. You can have anything as a function of u. That is what P of u.
Because these days, this polygons is quite impressive in this computational field. So, any structure, n-side, can it be considered as an n-side polygon?
Now, when you say n-sided, this is using 4 patch. But there is another method. This is called Coon's patch, which is represented for 4 boundaries. There is another patch which is general. Was saying that say there can be multiple boundaries, especially if you take the wing or fuselage. There can be multiple boundaries. There are 5-sided boundary patch, 6-sided boundary patch. The generic method is called Gordon patch. So this is generalization of the Coon's patch.
Okay.
So there, if you have say 5-sided, 1, 2, 3, 4, 5, 5-sided patch, 6-sided patch, you can use something like Gordon patch. But if the essential idea is the same, okay, like a Coon's patch. And from Coon's patch also you can drive because you have to cut. If you cut like this, right, you need to cut this. That's all. Cutting the parametric space, this UV space, and cutting in the trimming in the exosurface. Okay. So all that is doable. Main idea is interpolation of the boundary curve.
Yes.
No matter whatever is the representation of the boundary curve.
Thank you.
Thank you.
Yeah, thank you, Dr. Gaurav. We'll have a break now, like we will start after 15 minutes, and we'll try to complete our session in 1 o'clock. And try to manage your lunch by 1 to 2, and after 2 o'clock we will start a session on the numerical modeling by the Simmer Pack from Anand Padmanabhan. Okay. And 3:30 we'll have one more session of interactive session with our dignitaries professors and the earlier ex-director of DMR. Okay, thank you. Earlier research what I have done with respect to the repair and remanufacturing of the parts in the direct and deposition process. And also we have done some topological optimization to some aerospace brackets or some kind of the knuckle joints and other aspects. This is what the outline which I am going to give a brief what work we have done, how we can able to make use of the DD with respect to the repairing aspects and what kind of components we can able to repair and what kind of components not able to repair. As you are already know the basics of height manufacturing process. So David World has already discussed where we can make it terminology as a 3D printing or height manufacturing process. As we are going to develop the component by the layer by layer using 3-dimensional CAD models. That's what you are earlier it was because he is the founder as height manufacturing process. Earlier we started in 1980s making of prototypes. Now it's a direct manufacturing of any kind of a components. Directly we can able to manufacture near step components, or we can able to fabricate, or we can able to repair the components. That is not possible with any kind of complex components. That will reduce the time and as well as the wastage of the materials. That's what possible with your weight manufacturing process. But with respect to these thoughts, Professor Gore's thoughts, and as well with Charles Alva and the other big team members, over the next 5 to 10 years, this IT manufacturing will be a standard manufacturing technology. Now we are not much commercialized this IT manufacturing with respect to the industry scenarios. Many of the R&Ds are still going on in this IT manufacturing process. But with respect to some static parts, you might be knowing the leap nozzle that GA is having a patent is already going to be used with respect to the many of the industries. And that is already used and is already manufactured in all the aircraft. We are using that laser forward filling manufactured leap nozzle. And also many other static parts is also approved by the authorization of the quality and standard. Even the ASTM has approved. But with respect to even now medical, the knee implants or the hip implant has been approved to put it into the customized implant with respect to the patients. But to take the 5 years back, it was not approved. Because we need to see how much extent it is going to be affected. It is going to be beneficial for his life, or it's not going to be beneficial. There are several studies have been characterized and done, and even FDA has approved to put it to the patients. Even the India, many of the companies might be knowing the Incredible 3D and some other companies, Jejal Medical. They are making all our customized implants with our titanium materials. Titanium 64 is more biocompatible. Because of that, even 316 is also used in application where we can able to put like some kind of a screws or some kind of a plates. Especially with respect to implants, they are making use of the titanium 64, and that the grade 21 is biocompatible. And even the innovative designs is going to be enabled like a generative designs. That's what the topologically optimized designs, the generative designs based on your artificial intelligence algorithms, or which we can able to make use for our new materials. It is going to be a common when it is removed from the constraints of the traditional manufacturing process. Because that is what required. We are already fixed with the design aspects. Because we know manufacturing process steps. Because we have to make with the conventional, either casting, machining, or maybe extrusion, these kind of process. Because earlier we are not aware of this type of manufacturing process, how we can able to generate the new design and aspect with respect to the application. But now we can able to develop our own generative designs. We can reduce a lot of material wastage, and with respect to the application orientation, we can able to develop such kind of a generative design with our topological information. And that is only possible with our IT manufacturing. We can able to manufacture the components. And the innovative designs will be a part of continuously improving the process of production efficiency and as well as optimization. So that's what the direct manufacturing is, a IT manufacturing with advancement to the next generation of the 3D printing machines, which enables the scalable production at the very less cost. Because of the reduced cost, we can able to manufacture the scalable from prototype to the application parts. And advances in these printing techniques with respect to the digital materials are driving progress in the applied manufacturing as well as in the production science and as well as the production process aspects also. But when you see these, whenever I'm talking about the generative designs, that even the hexagon or the smooth fact or even end topology, these are the new software which are available to make some kind of a generative designs. But earlier, if you see one example of our piston head, it was made by the extruder casting and then machine was used. But now, can we able to print such kind of a part of the manufacturing process? Will it be sustainable to use such kind of the load and as well as the temperature and other aspects which we are using for the dynamic aspects? But there we are meeting a lot of challenges. Is it possible to adopt or ready or not? Because many of our constraints in the thoughts as till more than 40 years we are running in the manufacturing process, it cannot be used for the dynamic applications. Majorly we are focusing on the static parts. But if you take this example, is definitely the dynamic part. So there you can have a lot of fatigue loads is going to be applied on this. But one of these material 3D systems and even elemental 3D, they have developed these kind of the modified topologically optimized the piston heads, and the GT91 car they have already adopted this kind of a Ferrari car, this kind of a titanium printed piston heads also. And this is giving more horsepower than the solid pistons, and as well as it is the weight reductions that will improve the efficiency of the vehicle. That's what it is mainly focusing to develop these kind of the weight reduction, high strength to weight ratio, and as a generative design components also. And this is another some kind of a brackets which we can even we are using it for some kind of a sports bikes, the gaming bikes. These kind of generative design, it is very much required to replace with some kind of the existing parts. That's what we can able to do. But to generate these kind of designs, we need to understand what is the initial design ideas, which is represented as in the models, and then can we able to provide any kind of some new solution with same or maybe change with respect to the recommendations, and with that going to be evaluated to be suitable for the satisfactory with respect to the factor of safety or with other design considerations or with respect to other the loading considerations, mechanical properties. Then we need to provide some kind of a solution that the final design solution is suitable or not. That's how we have to think to make into a selection and generative designs which we can able to develop with respect to the existing components. And if you see, when we say the optimization, even generative designs, or when we can say the topology optimizations, first it comes our structural optimizations. Like it is a design techniques that uses our numerical optimizations and as well as to create the cost effective and the material efficient models of the structures. If you see here, this is what the size optimization. The initial component is very big and then we have optimized to minimize the size, and it may be a shape optimization and it may be a topology optimization. Now we require these kind of topologically optimized component for the real-time applications. If you see some kind of a chair designs or the bench designs, earlier we have having a concept to make it these kind of parts. That is how now we can see a lot of generative designs, optimized designs. Those are more attractive and as well as easy to manufacture and as well as the minimal cost we can able to manufacture. That's what if you adopt our new advancements and technological development, then we can able to generate these kinds of attractive developments. And if you see then coming to this topological optimization, which is a powerful optimization approach, it can able to create innovative designs. If you see one example here, this is some kind of a bracket, structural bracket. This was we are made by the machining and as well as with welding and to make this kind of a bracket and then we have made with several holes by the drilling and but this costs almost one part is equivalent of 5,000 rupees. But can we able to change the designs and we can be able to make it very lightweight and improve its performance, which may be used in your aerospace, or may be used in your automotive aspects, or it may be used in architectural aesthetic appearance also. Yesterday the professor has showed one of the connection joints which can be used to give a more aesthetic appearances. Like that, we need to think how we can able to modify. That's what your other people and in our one of the schools, topology is the most usually softwares and as well as another one is the example. They have tried to simulate it where the load is acting on this modes and where the structural part is existing, and with providing the several constraints and as well as material properties. And if you see, this is what the optimized raw topology optimization. But raw will be not be efficient to manufacture with respect to your ready manufacturing. We need to do some kind of smoothing to make it be a more attractive as well as a finished part which can able to use for your ready manufacturing process. That is one of the component. It will save a lot of the weight of the component and other. The another one, if you see, this is what the hexagon, the collision. They have made this kind of the part by the topology optimization with the MSc software. They have started with the design and they have made with several iterations with the FEM to make which is the best optimal solutions. And how we can able to print that part, because topology optimization gives a lot of generative designs and it can able to minimize wherever the load is not and wherever the situation is not there. But will it possible to print and what orientation we have to print it? That's a major challenging issue also is going to come in our topology optimization with respect to IT. That's what they have made and they have provided a lot of support structures. And another one, if you see here, the reference finite element model, and then we need to perform the design. Then we have to do several iterations to get it to a redesign, validation, and then we have to go for the topology optimizations. That's what the key consideration is. The reference FEM is a crucial tool to compare progress in the mass production, stress factor, and as well as the factors. That is what required when we understand the topology optimization of the design scenario. And after if you able to make that product with the manufacturing, then you can go for the real-time component manufacturing, maybe with respect to metals or maybe with respect to the particular component what material is made of. And if you see one study with our undergraduates we have done, this is what the original component of an engine market. You might be seeing in your lot of publications are also there with respect to this. Lot of topologically optimized designs also. But can it be redesigned more efficiently than the existing designs? How much extent you can able to save the materials and as well as to improve its existing performance. And I show you this is what the existing designs from this they have published already in 2021, and this is what the optimal design they were saying. But with respect to our ideal, how we can able to redesign it more attractive manner and minimal cost, minimal wastage of the materials compared with the published or the existing components. This is what the data we have taken and we have tried to do the topological optimization with our top as well as one another software is Altair, and as well as even with the ANSYS FEM we can able to do the topology optimization. We try to compare all these kind of models with the different softwares. This is going to be a best solution for making topology optimization and as well the weight reduction. This is what the component we have finally got with our the top and as well with the another one is the hexagon software that MSc market. We have got that final optimized technique in bracket and we have made with our initially with the PLA polymers with the FEM process, and then finally we have printed with our ready manufacturing, the board bed feature process. This is where in this orientation we have provided very less minimal structures, minimal support structures. Because when we wanted to print orientation is very important aspects, because it will generate a lot of heat accumulations in the part print. That is going to create a lot of deformation during the printing. And as well as if you do not provide support structures, there may be a chance of the delaminations and it's going to heat up and even maybe going to create some kind of cracks in the printed parts. That is where we have tried to understand in which orientation is going to be best. That's what we have printed with minimal support structures. And if you see the another part, this is what the vehicle which is used for the terrain for bachelors, they can able to go for different kinds of competitions. This is what the initial knuckle. It was the existing designs. It's almost the weight is model is 0.75 kg. Then this component can be able to minimize because their weight is the major constraint in such kind of a knuckle for the terrain vehicles. But they wanted to reduce the lot of the weight of the component. Then we started with how we can able to redesign it. Where and all the loads and as well as the factor of safety we have considered. And this is what we have done with the several iterations with the FEM and as well as NPOM. And finally we end up with the optimal designs of the 0.276 kg of the component. Means almost we have reduced 65% of the weight of the components. That is what it is required understanding of the topology optimizations. How much extent we can able to reduce the weight and as well as considering the safe factor of safety and other stress distribution of the mechanical properties. This is where it is very much important aspects. And other with respect to advanced simulation technologies, with respect to evaluating your ready manufacturing produced parts. That's what we need to simulate and as well as to predict and minimize the distortion defects in the part which is produced by the ready manufacturing. If you do not understand the simulation aspects, because we have to do several iterations to find out the optimum process conditions. Because we cannot able to run all the experiments with all kind of materials. Yes, we need to know what is the optimal process conditions which we can able to print. Even if you might be aware that if you print some kind of a cubes with the optimal conditions, that may not work for your real components. If I want to make some kind of a small bracket, if you use the optimal process condition which you have made for the cube, it's not going to work for your some kind of a bracket. What will be the challenging issues we are facing? Is it only the process conditions, or is it only the part print orientations, or it may be with respect to the deposition strategies? Even though you may be considering the deposition strategies for the simple cube, because it's a complete solid cube, and where you are going to give a lot of deposition strategies, hexagonal scan pattern with different linear, bidirectional, just a lot of scan patterns you can able to optimize to get to a best density. But the scan patterns also plays another important role to distribute the residual stresses in the part. But when it comes to a brackets or some complex components, they need to think of what kind of scan patterns, strategies we have to apply to fabricate the components. Because simple scan strategies may not work with respect to the complex components. That's what the major aspect is. This is where simulation enables to calculate the thermal models as well as mechanical and mechanical changes during happening in our ready manufacturing process. That simulation tool will help to verify the AM parts to meet strict quality and its performance standards. Right? They reduce the need of trial and error designs which you can able to do with your printing. Because you might be buy the machine from the 3D systems or maybe Trump or maybe the other concentrators or DM3D and all. They will give you the standardized optimal process conditions for only for a few materials. They might be giving for titanium, they might be giving for stainless steel 74 pH or maybe aluminum or maybe even inconel. Because this is the major materials, the work, the research aspect has been done in these materials. But if you want to give some kind of your customized materials, if you want to make some kind of a bronze, if I want to make some kind of a gold or some other materials, the lot of research data which is not available to feed into the optimal process condition into the machine. Well, sometimes what happens, whatever the process condition they are given, which will not be sourced to your materials, because we are not buying the raw materials from that manufacturers. Because we are using our own raw materials for using into our head manufacturing machines. Because the powder distribution, what kind of powder quality we are using, that's also going to be major challenging issues when we optimize the process conditions. That is where it is required. We need to understand the numerical modeling to simulate to understand how efficiently we can minimize the trial and error aspects, the design aspects. And the high fidelity of the simulations which will provide the detailed insight into the melt pool dynamics and as well as the phase transformation, which is crucial for our certified parts in the aerospace and as well as the medical industries. It's what it is required, especially in the aerospace and the medical industries and all. And the physics-based simulations, because we might be doing the FEA with the with the analysis and all. So very much essential to assign the quality and the conformance of our manufacturing. Because you might be knowing nowadays there are a lot of the in situ monitoring and they can able to give the feedback signals. In what way they are going to give the feedback signals, in what way they are understanding your application of the machine learning that can able to detect the multiple temperatures and as well as to adjust its laser power as well as the scan speeds. Because you might be knowing the one component if you want to manufacture your laser power, scan speed is the major important factors. That's what the process map yesterday Mr. David has told you. Process map is going to get the optimal process conditions where you want to have a high mechanical properties and as well as the geometrical components with minimal defects. That process map, when we are going to develop, we need to understand a lot of application of the machine learning. But how this machine learning feedback signal is going to give into the systems to adjust your laser power as well as the scan speeds. Because once the part is going to be developed for the several height and then the heat accumulation is also going to be very high. Then we need to optimize the laser power is very important aspect with respect to the scan speed. And if you do not optimize this scan speed and the power, then you will end up with a lot of thermally induced and as well the deformed parts in the ultimately at the end. That's why it is required to understand the physics-based simulation aspects. And simplified simulation models, especially for the powder bed filling process, which is going to be a predefined libraries will be there, even the thermal strain data will be available in the, because nowadays for the PVF is a lot of work has been done and also numerical studies is also done. But with respect to DED, very minimal work. They are trying to adapt with our welding technologies. How we have done for the TIG welding or MIG welding, same kind of way they are trying to adapt. But when we consider with respect to the laser powered ED process, if you consider the welding process, almost 100% of the material is melting and deposition is taking place. But with respect to laser powered ED, only 40 to 60% of our powders are melting and the solidification is taking place. Because how much, whatever the reflectivity of the materials and whatever the absorbability of the materials and how much lossage. Here the multiple formation is different than your welding. And compared to welding, the rapid solidification takes place in your the laser DED process. That is where a lot of challenges are with respect to the laser DED process and even the fully coupled thermomechanical simulations, which can incorporate the scan data to generate the thermal profiles that drive the mechanical analysis with respect to improving the distortion detection and accuracy and all. Even the high fidelity model that can able to simulate the complex manufacturing physics of the multiple and as well as capturing the phases and the solidifications and as well as the microstructure evolution. Nowadays we are having very advanced numerical model you can able to understand as well as the microstructure which is going to be developed in the manufacturing complex. This way we are trying to. And even the multiple machines, process and as well the materials to define our game environment today. Because very long IT manufacturing has witnessed strong growth since from more than 40 years. We have a strong focus shifted from the prototype to the manufacturing of the components, the functional components. But the critical challenges is still persist in the industries, including the build repeatabilities. Because if I want to print one component today, tomorrow if I use the different powders or the different machine, I am not going to get the repeatabilities. Build repeatabilities or the process scalabilities or the stability of the DED process or the LVP process. Why we are having these challenges with respect to repeatabilities? Is it because of the process or is it because of the raw materials? Or is it because of the optimal conditions what we have set into the machine to fabricate the components? Even if you take, there are several manufacturers. Yesterday I showed DED machine manufacturers, even the India VFW is manufacturing, and even the crump laser is there. If I make a component from the crump laser as well with your VFW, both we are going to get a different as well the VFW aspects, the components strength as well as in the other aspects. Is it because of the process or is it because of what we are trying to understand and optimize the process conditions? Because we need to understand ultimately how much G by R ratio. That's what completely with respect to the microstructural aspects. With respect to the solidification as well as cooling rate and how much energy density we are using, as Professor has mentioned, you need to use a very high energy density which is less than the pure formations to get the better mechanical properties. Even you may using optimal energy densities to fabricate the component, but that may not going to get the higher mechanical properties. That's what we need to see the quality of powders which we are using for manufacturing and the energy density which we are using for manufacturing the part, whatever is the machines which we are using. That's what the critical issues or challenges are still existing. That's where advanced digital tools are addressing these kind of issues with like generative designs or the lattice or even the hardware integrations or even maintaining the distortion as well as the shape compensations also. The AM has a greatly expanded with the multiple techniques and as well as the technologies to meet the diverse industries and as well the material needs. Because whatever materials which we can able to make to solidify, all materials which we can able to use in your manufacturing process. There was no kind of a constraint with respect to designs or with respect to the materials. That's what we can able to meet the diverse industries as well as the materials needs. And even the indirect, that is in the direct in the deposition process, the molten material is deposited to the nozzle, either maybe on the multi-axis or maybe on the CNC machines also, with the deposition heads also. That's why we can able to deposit the components with different aspects also. Each AM process is a family of a specific raw materials. That's what maybe powders or wire or maybe the ribbons, or it may be using with respect to the different the material types, maybe plastic materials, metals, or maybe ceramics, or maybe even composites. That's how that 7 categories have been categorized. Even in the DED process, direct deposition process, we have several categories. That's what we can use arc, or we can use laser, or we can use as an electron beam also. But with this, all the 3 processes are suitable for kind of all applications. Where we have to choose your laser DED process, and where we have to choose your arc based DED process, and where we have to choose your electron beam manufacturing process. All the concept and the mechanism is same, except we are using a different energy sources and as well the different feedstock materials. Either the powder we are using or either the wire we are using. But one example he has shown in the Amsterdam, the bridge which is made by the wire manufacturing process. Can we able to make such kind of a very big bridge with your laser DED process or with your even the laser wire DED process? It's not possible, because where we want to go for a very structural components, very big structural components, more than 5 feet, there we can able to use your wire manufacturing process, because there we are not much worried about geometrical aspects, geometrical accuracies. We are not much constrained. In such cases, we can use our wire cut manufacturing to make the components. But where we want to have a very preciseness and the quality aspects, then we can come back to our laser deposition process. If you see here, some of the component is already existing or maybe made by the cold bed fusion process. I want to add just additional feature onto the existing components. Then I need to go with our laser DED process. one of the beam technology, that's what now they have added. They made a forward manufactured component with along with the additional features. If you see, these are the features which is added with the laser annealing process. Means any kind of existing components we can able to repair, or we can able to add additional structural aspects, additional features it can be possible by the laser annealing process also. And if you see, how does this direct annealing deposition process will work? Because I am not going to go explain this, because you are already aware that how it works and how process we can able to make it. This is what the different technology and the heat sources and what are the methods which is used in today with respect to all kind of this direct annealing deposition process. And if you see, this is what with respect to some kind of implants, medical aspects. Yesterday some of you are having questions where we have to use electron beam direct annealing deposition process, where we can use electron beam powder bed freezing process, because it's highly expensive, because we need to have a electron energy source and we also completely battery, because whenever the part we are going to manufacture the electron beam, definitely it's going to be very expensive, because we have to maintain the atmosphere as well as the energy source what we are using. You will see such kind of a components where you can majorly use for your medical applications. And if you want to see the arc based wire arc based, you can use for commercial applications. And if you want to make with the laser wire or with the powder DD process, these kind of a part which can be used for repairing or maybe name and shape components also. But nowadays the metal has come up with lot of advancements. Even the is going to talk about in the tomorrow, the hybrid technologies. Means the metal has that capability to make the component as well as to machine and as well as to develop additional features under the existing components. In the same machine, they have put the CNC milling and the drilling as well as with respect to the wire-based depositions. But if you compare these two technologies with the wire, the deposition rate is low. Because even if you go with 36 kg per hour in wire arc activation and manufacturing, but here we can go only maximum of 2 kg per hour. Almost 2 kg we can able to melt and deposit in the laser based compared with the arc based. That's why if you see, this is what the lens or maybe the RPM industries have made some kind of a aerospace part with the lens with the atomic and it's most cost effective and with limited materials which we can able to fabricate it. And if you see with respect to this laser based, even in our concept laser we have done a lot of studies to fabricate the name shape components. One we have tried with this injector head. This was worn out in the some of the aerospace part. They were trying to repair it, how we can able to repair it. But initially we tried with the TIG welding process. Can we able to repair it? But there we are end up with lot of geometrical difficulties, because our arc has to deposit in that controlled chamber as well as one with respect to controlled geometrical aspects. But then we have come up with the laser annealing process. You see, this is what the final finished component and then we have developed these scan strategies, as Professor Gora has discussed you, how we can able to generate the scan strategies. We have taken the three-dimensional the errors and the defects in the parts. You might see here we have given a deposition strategies in this manner to deposit this kind of a part as well as this another half section of the part. But where we are having the intersections at these junctions, there we are having a lot of defects. This is mainly because of the interpolations of the deposition at where it is interacting from the one scan strategy to the another scan strategies. Definitely at this particular location we are having a lot of reports the defects which we have faced in the issues. To address these issues, we have made several iterations to bring it back to the normal, to the effective. We use our laser reading process for the applications. Different type of strategies we have adopted. Instead of this going for this linear strategy, we adopted different kind of scan strategies that can able to minimize these kind of defects in the thermostat components. The another one, as I told, electronic manufacturing process. The SIAC has made, if you see, you can able to see the differences between this laser reading process and the electron process. See, the quality and the finish what we are getting and the surface oxidations, if you maintain carbon atmosphere or to use in a open atmospheric condition. Because as this is the stainless steel we have done in a open atmospheric conditions and with the nitrogen as a productive gases. But if you see a lot of the satellite particles we are sitting under the surface of the part. But if you see the finish of the part which is made by the electron beam, are very good surface finish and also having a low residual stresses in this EBM process comparing with the laser reading process. And also we are having a high deposition rate compared with the laser reading process. That's what we can able to use even for the suitable for the large scale components. And but only the thing is here we have to maintain the vacuum environment. Because when we have to use for the electron, should be a vacuum environment is required. That's where the cost of equipment goes very, very high. Initial cost of the equipment is very, very high. And if you see the another thing is this is what I wanted to mention. The laser wire reading process, the multi-volt as well as the PFW aerospace in the Germany, they have made a lot of developments with respect to the wire-based systems. Earlier it was using only the arc or using the electron beam to melt your wire-based and all. Now they have made laser wire. This is what the hybrid technology I was talking. You see, this is what the milling head they have as well as the deposition head they have. In the same process, they are using a laser wire-based DD process. And if they want to machine the component and further they want to deposit additional kind of additional features onto the existing component, they can able to mill it and they can able to additionally deposit the additional features. That is what with the material system have this hybrid technology system. And if you see the quality of the component, means this kind of component directly you can make use for the applications. There is no need of any kind of post process. Means this is what the one ring is there, and that ring they have added additional features on that. Means directly they can use this kind of the electron beam based or the laser wire beam based components for the real time application without having any post processing aspects. That's what possibilities with respect to this hybrid manufacturing. And if you see, especially when I am talking about the repairing, these are all the additional features we are adding into the components. But when I am talking about the repairing, the same mechanical properties or better mechanical properties than the original part. Where we can use the reading process very, very cost effective to qualify the components for the repairing aspects also. But for these aspects, we need to understand what are the supporting technologies which are existing. Means if you see the tool-clad cam tool for strategies, or maybe even touch pro with respect to your CMM, or maybe the thermal controls. Means during the depositions, can be able to control the temperature, and if you are able to provide some kind of a coil system to maintain the temperature during the depositions. And these are some case studies we have attempted. If you see, the one drawback is one of the gas turbine casing and all, they made the holes in a different diameters what is required actually. That's what made by the machining and all, but it is with the nickel based superlizer and all. But how we can able to repair it? Either we have to throw the part or we have to manufacture once again, or we have to repair it. But the repairing is only possible by our laser reading process. But again, challenge is repair of incorrectly making holes on the outer circumferences to avoid some kind of scrapping of the parts. Means we have added the solution to deposit the 30 by 30 mm of the patches in the entire part. Then again we have to delete the required dimension of the diameter. That's how we have taken the data and then we have repaired it. And another case study is if you see some of the forging molds, because in the forging industries, molds are keep on warm because they are going to give new kind of molds. Because once certain life of the component of the molds are worn out, then they have to throw it and they have to use the new molds. But here, can we able to repair such kind of a molds? You see the worn out part of the mold here. This is the hard forging process. And this is what the after the part has taken, we have done the machining, complete machining was done to make it to remove the such kind of unnecessary the worn out parts and all. And then we are trying to generate the data how much scanning which we can able to get from the worn out mold and all. And then we are trying to understand how much extent the material has worn out on the molds and all. And then we are trying to reproduce, and then we have measured with your 3mm. The complete entire section is also milled, and then we have added additional materials with our AD process, and then we have finally finished with your milling process to get the repairing of this mold. And this mold has successfully used for another the making of 10,000 of components of the forging parts. That is where repairing is very much beneficial with your laser annealing process. But with the other kind of technologies, repairing of these parts are very challenging and we have to throw it away. And apart from this repairing, even we can use for the laser cladding. If some part is worn out, or if I want to improve its performance, or if I want to improve its corrosion properties by hard facing, I can able to add additional corrosion resistance materials or to improve its wear resistance materials. That's what we can able to add by your laser cladding. With the same laser direct integration process, but we can able to add with the additional materials to improve its performance. But the main advantage is you see we can able to maintain the geometry which is in a critical and heat sensitive components and to avoid our secondary process. Some kind of additional process we can able to minimize it. And as well as we can able to reduce the grinding requirements and the overall finishing costs. Complete overall cost of manufacturing we can able to minimize, and we can able to achieve the high quality of materials properties with less than 1% dilutions. That's what possible is for laser DD cladding and other repairing aspects. And even it can ensure that the minimal heat affected zone is possible with the laser DD. Even you might be having some thoughts, can we able to repair even with the welding? The TIG welding process we can able to repair it if it is a part is very weak part is worn. Yes, we can able to repair it, but the heat affected zone and the thermal distortions are more in the TIG welding process. There we can have a lot of difficulties in the mechanical properties of the repaired parts. That is where we can able to use, we can able to use our laser DD process. Even the small internal diameters of less than 1.5 inch we can able to repair with the laser DD process. That's what possible with the DD process. And if you see, these are all the components they are made by the repairing with the conventional methods or with the laser DD process. These are the methods, and as well as some of the advantage compared with the other kind of welding technologies. And even we can try to use for the hard facing, because earlier we are trying to do some kind of heat treatments of the valve stems of some of the turbine, steam turbine shafts. But the steam turbine shaft which is going to be warm, but how we can able to repair it? But that repairing is possible with your laser direct integration process. Means the challenging is depositing a hard facing material on that stems. That is a very challenging issue. There we can use our the DD process, the triboloid cracks at speed, because it is going to create a lot of cracks when it is going to expose to a high temperature when the melting and solidification is taking place. That is very difficult to weld. But to maintain a temperature of preheating temperature of that the steam, the turbine shaft up to 550 degrees centigrade, then we can easily deposit the laser DD process the 10% of nickel, which will enable the crack-free processing. That can improve its life of the components, and we can also produce a new crack-free repairing techniques with our laser DD process also. That's what hard facing is very much useful in aspects of erosion, corrosion, or maybe even cavitation, and even the hard facing aspects. That's what people have done with one of the components with the laser DD process. Laser wire DD process, they have developed the satellite 6 on the laser cladding of the shaft, and they have made, after laser cladding, they have machined it, and then they evaluated any kind of defects after cladding which is existing in the component or not. That's what they made with the dye penetrating testing to evaluate what kind of the quality which we are getting by the laser cladding process. Means this is a high quality of satellites over the surface of this disc they have done, and they got a very good quality components. I will not run that video. You see another components. Another case is nowadays major challenging is the Pelton turbine circuits. The RAM lab has recently made an attempt to repair such kind of parts, because lot of the erosion is going to take place in this kind of the Pelton circuits. But repairing of these parts was not at all made in a real case. But now we can able to repair these kind of parts by our laser wire DD process. They have made to address the issues. This is what the worn out area. They have taken this kind of a Pelton bucket surface area with the 3D scanners, and they have tried to understand how extensively worn out has been taken place, and what is the volume, and what kind of deposit strategies we have to use for fabrication of repairing of these parts. Because Dr. Gowda told you can take the data, but when you try to repair it, it's good. Because how your scan path of a deposition strategies has to be deposited. Even during that, it may be going to create some kind of defects also. But there is where they have made lot of attempt to address, and this can be repaired in 1 hour, 3 hours within 28 minutes of your arc time. That's what very minimal cost they have repaired. This is what the repair component. That's how we can able to take the data and we can able to repair it. And if you see, this is another component. They have made the scanning along with the depositions and all. If you see here, however, the scanning data will work, and as well as the repairing data in the same robotic arm of your laser DD process also. If you see, this is what the 3D scanner they are attached with your robotic welding. That's what with the laser DD process. The RAM lab, it is going to take the entire speedy data of the scanning of the three-dimensional data, and then immediately it will encode it to how much the worn surface area, where and how material we have to fill, and then we can able to deposit in the same machines the additional layer of the material which you can able to add it. That's how they have made RAM lab with the new kind of developments in the CM systems. But now we are having in our other systems is we are taking the data, we are processing additionally, and then we are developing a path planning, and then we are going to rebuild or develop additional materials. But that is what the advanced technological development they have made with in the same systems. They can able to capture the data and they can able to repair it. But another aspect, if you see the repair with respect to the new make, is it going to be beneficial when you consider the repairing of the existing component? What is the cost of repairing, or what is the cost of if you want to make the new component? If you see here this gas turbine maintenance requirements, because the gas turbine maintenance requirement is very high. It is dependent upon the independent counts of the start hours and as well as the what kind of methods the UHS maintained. And the first stage of the nozzle we are preventive maintenance of the repair with respect to the replacement economics. If you see how much the nozzle has been worn out of this gas turbines and all, means if you reduce the 10% weight reduction from 10 parts to 1 part, or if you improve the efficiency of 30%, or if you make some kind of a unit reduction by 75%, or maybe you are including some kind of a durability of that product also. That's why it is required whether we have to go for a complete replacement of the part or you want to repair the existing part. Repair will continue until the part cannot be restored. That's what the minimum acceptance standards are. The repair cost exceeds the replacement of the cost, then only we have to go for the complete replacement of the new part manufacturing. And the other thing is, if you see, this is one of the aerospace they are made with G and the pattern with me. The Srinivasan has been worked on this one of the materials. These kind of additional features they wanted to add. If you see, this is the worn out part here and as well as here. You can see this is the leading edge damage on this your aircraft. So, boron cobalt alloy and the gas turbine unit. But the repairing of this part is, even with your laser reading process, is very challenging. Because when you see this kind of part is casted and machined, the microstructure of that part is equiaxed. But when we deploy these kind of additional features onto the existing part, we are going to end up with some kind of the columnar dendritic structures in that. But the mechanical properties are not going to match. Then again the part is going to be worn out very quickly even if you repair it. Then what kind of solutions we have to provide? Then they have made some kind of a DFT nozzle joint with columnar dendritic. If you see, we can able to differentiate this for the existing nozzle with dendritic structures, porous dendritic. And then at the interface, what kind of the grain growth is taken place and how we can able to break that columnar grain growth. This is what we have to address to maintain the same kind of properties in the fabrication of the component. If it does not maintain the same kind of the mechanical properties or the microstructural aspects, then even the repairing does not make any sense in the repairing of the components. And if you see, the other part is they have made the stick spirals with the nozzles in the oil and gas industry they are using. This stick spirals has worn out and all, but how we can able to repair it? Because it's very hard. You can see that hardness is 278. It's very hard and all, but with these ash alloy they are made with additional depositions, and even you can able to change the geometry of that spirals also. That's what they have made. If you taken the data of that three-dimensional, how much the wear has been taken place, almost 70 micron, 100 micron wear has been taken place on the spirals and then they have tried to attack with the different kind of the lots, whether we can go with the lot 1 or lot 2 or lot 3 or lot 4. Which is the best we can able to repair such kind of the spirals with addition of the materials which we can be able to repair with efficiency. That's what with the lot 4 they have made a very efficient repairing of that spirals. Even that will qualify for the DMTD productions and with the modified design spirals with the examination of that raised joints, which is going to be okay with the improved NOx emission and all. And even with cost saving via the scrap elimination, comparing if you want to scrap this kind of spirals and all, that's going to be a repairing is a very best advantage comparing with this scrapping of this kind of parts also. Even you can provide some kind of a new alternatives for this kind of the turbine designs also. That is also possible by the addition of this designs with respect to the existing components. Another part we have tried to make repairing is this kind of the defective turbine blades. But if you see, this is what the chopped out of this defective turbine blade. We have taken the data of this chopped turbine blade, and this is the only part we wanted to add onto this bottom part. But when we taken the data, we have taken entire data of this part, complete data of the part. When we are having the original design of the part, and then we have subtracted how much the part has been defective in the blade. Then for only that much of part, we have tried to develop a scan strategies or the deposition strategies. But for the existing direct part, we cannot able to repair it. Because we need to provide some kind of the machining, the milling we have done to make it easily we can able to deposit the addition of the materials. Because if you see, the surface is not completely regular. The surface is having some kind of a projection, some kind of a non-regular planes and also that kind of planes we have made milling and all. Then this kind of the deposition strategies we have provided, then we have ultimately repaired a good quality of the components also. That's what we have made with this kind of a turbine blades. The another blist if you see here is what one of the blists which is worn that also we can able to repair it. And if you see the another part is the case flange. The flange does not have some kind of additional aspect that can also be added with additional features with this kind of a part. And if you want to make some kind of a multi-materials mode dice also, you see this is another case study with the laser forward ED process also. You see this is what the initial part which is water, and this is what is the final part. And even this kind of a part which you can able, this is the deposit, and after that we have done the machining to get it to the original shape of the components. And major another challenges we address with the crankshaft, because crankshaft is normally going to be worn out. Because you might be knowing after 10,000 the run this crankshaft is going to be worn. But how we can able to repair that complete data we have taken, how much it is worn out with the 3D scanners, and then we have tried to add some kind of the margin steels and as well as the chromium magnetic steels, and then we have deposited to get the repairing of the crankshaft. And so we have tried to make with applications of the laser DD process for the repairing applications. And if you see the another aspect is, if you see the bottom is copper and the top is some kind of a tool steel material is deposited. That's what the 400 material is deposited on top. This is what it is required, because when you use the dye industries applications, we need to provide a lot of cooling. Otherwise, dye damage is going to be take place. Because if you provide a copper material, this is having a high amount of the thermal temperature resistance. Because it will dissipate very heat very quickly compared with the other materials. But here we are in the top surface, we need to have a very high hard materials which is having a high strength also. But the deposition of these two metals is going to be challenging, because at the interface we will end up with a lot of portion of thermal expansion, and the defects are going to become, even maybe deformation is going to be. But for those aspects, we have added an internal layer, that's what the monel boundary is used between these two components for this molding part. That is going to be acts as a buffer layer between the tool steel and as well the base part. That is going to give an improvement in this the functional grade mold, which can improve the efficiency 30% and as well as 80%. That is where it is required for repairing of the molds and all. And with respect to all these things, as I told, whether the repaired part will have the same kind of mechanical properties or not. How do we have to qualify? Yes, we have done the repairing. Is it having the same mechanical properties with respect to the substrate? But that is what we have done in the initial preliminary studies with respect to some of the titanium alloys. We have taken the data of the surface deposition strategies and as well how what kind of surface finish we are having and what kind of microstructure we are getting. Initially tested coupons we have printed, some kind of a 10 mm by 10 mm or maybe 50 by 50 mm coupons we have printed. And we have measured what is the melt pool at different locations of the entire fabricated components, what is the axe spacing, what is the columnar structures, as well as the size of the structures, grain sizes and all. And we have tried to analyze with wrought materials mechanical properties as well as the only deposited material mechanical properties with the different orientation you see in the build direction as well as in the across the build direction. That's what if you see, this is what with respect to horizontal, the vertical depositions and the 45 degree inclinations, and this is what with the half section of the repair and the rod line, and one cross section and another with the two cross sections. And we have compared all the mechanical properties with respect to strength, hardness, as well as the elongation, even the heat fatigue properties also we have tested. Because ultimately, once you understand all this data, then only you can able to use it for the repairing applications. Otherwise, it is end up with a different mechanical properties, or even if it is repaired, it may not be useful for application. That's what if you see the strength is matching with the wrought materials, except the elongation, the strength as well as the the tensile strength and ultimate strength is matching with your art materials. But only the evaluation is not matching because we are having a lot of the porosity defects. But these porosity defects, even the optimal conditions you are using, which we cannot able to minimize. Because in additive manufacturing, porosity is a common aspect, but to can we minimize this, we have to go for the cooking. After this deposited component, if you keep it, we can try to improve its elongation properties, but not as extent of the rotolase. We can try to match near to the rotolase, not it can be completely same as the rotolase. But that is why by the dipping process we can able to minimize it. And also we have tested, that's what I told, the fatigue properties and the crack propagation properties also. You will see that fatigue properties in all the conditions with respect to rotolase, even in the crack propagation which is matching. Then we have tried to address how we can able to repair that from the real component. And repairing are also challenging because the data which we have taken, the CT scan data of that existing component could not able to repair it. We could not able to generate the scan strategies for the component. Then we have made additional milling to create our own defects in the defected part also. This is what we have built it, and then we have taken the data, and then we have tried to generate the data for our build defective data, and then we have repaired by the laser reading process. That is how we have made to repair the term of the automotive titanium components also. This is what to qualify all the things we need to understand that after mechanical properties, microsectional, then we have to go for repairing application. That way we can majorly use for our laser reading process. With respect to another some of the things I wanted to just show you quickly. With respect to WAM process, we have made several studies and that. You see, quickly I will go to this. I will not come to this. These are the some of the big parts it is made by the WAM process. And if you see one of the die designs, they have made with WAM. But if you compare this WAM process with your DD process, laser powered DD process, it is going to be more beneficial when you want to repair the dies and all. Is the laser powered DD process is more beneficial, or laser wire DD, or maybe arc DD process is beneficial?
You have to compare the efficiency or the
in terms of the quality, because especially in the die industry, we need to
where do you
powder LED?
see lasers is both we can use for the wire as well as for the powder. But when you go with the powder, its complete repairing of that part is difficult, and as well as it's going to be a more expensive compared with the wire based manufacturing process or with the laser based wire DD process. But if you compare with only with the wire arc as well as the laser wire DD process, laser wire DD process is going to be a good mechanical properties and having a good quality of components, and even the post machining is minimum. But if you use your wire arc manufacturing process, it is a cost effective process, but additionally it will add up post machining aspects. That's what we have tried to attempt to making such kind of a dice and all. Okay. And another thing, I will not show these things because Professor already showed. If you see, the another thing is we can able to make bimetallic components. In PVF, making a bimetallic components is highly challenging. It's very difficult because we have to mix the powders, or we have to end up with the scrap of the powder particles. But in DD, without losing the powder materials, we can feed n number of materials when we are having a more number of feedstock materials of the hoppers and all. In the same material, we can able to provide bimetallic or even the functional grade materials. We can feed into the nozzle, coaxial nozzle if you are having a multiple hoppers. You can one hopper you can feed the titanium, one hopper you can feed the copper, and another hopper you can feed the aluminum. You can combine, you can able to fabricate the grade structures or even the bimetallic structures also. And another component is, if you see, this is what the fabricated components with your wire are. but ultimately we need to go with this is the machine components. For one such kind of applications, we have worked for the stereo aerospace when I was doing my postdoctoral things and all. This is one of the big robotic system with wire rocket manufacturing we have used. This is one of the big ship propellers is manufactured with marine steel materials. And another one is we have made with this is what the major component which was already tried to implement into the aircraft brackets. The door which was made by earlier the fastening and as well as the sheet metals and all. They are using lot of the spot welding and as well as the fastening aspects. If you see the right hand side, this is what the aircraft door bracket will be. But they want to minimize the weight of the reduction. They want to reduce lot of the weight, can able to improve the efficiency. And also need to have the same quality of the strength. But we have started with manufacturing with your wire rocket manufacturing process. This is what the component we have made. You need to see lot of the delaminations and deformations are existing. This is what we have taken the plain sheet and we have made try to manufacture the different kind of the walls and all. But even at the junctions you can able to see a lot of defects are existing. But we have addressed all these issues after several attempts by considering different path planning strategies and what kind of axis, whether we are using 3 axis, whether we are going with 5 axis, and how the scanning or deposition strategy. You see, even after machining, you can able to see a lot of cracks. This is what the deposit components with these kind of deposition strategies, but we are end up with the defects. But with all these kind of understandings, we have made the efficient defect-free component for that kind of a stereo aerospace and all. And if you see, this is what the final component we have made. If you see, this is what the final component we have made. Means we have addressed how we can able to fix our plate without having any kind of deformations. Means that will minimize the residual stresses and have the accumulation. But for these, we need to change our path planning. Earlier, what we have gone for the linear path planning is not suitable for this kind of a component. Then we have tried to address the non-linear path planning. Then we have made it. There is no delamination which are occurred between the plate or the depositor things. For this, we have also made several holes to distribute the heat accumulation in the parts. What I try to say. And another aspects also we have made some kind of a ducts. You see with 3 axis what defect we are facing because of the 3 axis tool paths. And if you go with the 5 axis tool path, you can able to efficiently fabricate this kind of attacks also. That's what if you understand this the CAD bed models with the different kind of slice based neutral axis with respect to the closed axis, you can able to fabricate the efficient components also. The several understandings which we have also made with different studies. It's what just with respect to the wire based arcade manufacturing process. Okay. Thank you. I will end up with this talk. So after 2 o'clock we will start. Okay. If you have any queries, you can directly ask me, and we can discuss with you last time. Okay. If there are no queries, for the lunch, 2 o'clock immediately we start for another session for the maximum factors in the as well as provides. Thank you.
12 years of experience in the CAA and structural simulation domain. He holds a bachelor.
CSM Software Private Limited. And from there, Soleil, which is a Japanese company, had acquired this particular CSM Software Private Limited. And hence, from there on, we have been known as Soleil India Technologies Private Limited. And for our talking about our services and solutions, we offer product design solutions as well as testing and validation solutions. Design solutions, we are a leading partner with Dassault Systems in India, basically for CAD and PLM technology distribution. And coming to the CA front, in the technology distribution, we are a top level partner of Hexagon or the MSC software product. So, this particular tool, Simultac, which we are going to talk about, comes under the CA distribution technology, which is under Hexagon. Okay. And we also have engineering services divisions in our corporate office at Bangalore, which is offshore CAD as well as CA service from India to customers around the world. And we engage with MNC's global design operations as a sharing engineering center. So we have the services aspect as well as the technical support aspect in the corporate office. Okay. So this is basically basic overview. And our main customers include government companies, mainly the aerospace companies like HAL, NAL, and several government companies, as well as automotive companies, academia, as well as engineering services companies also. So this is a basic overview of our organization. And coming into Solaris India, we are actually 30-year-old customer-centric organization with about 1,000 plus customers, and we offer a reliable solution in digital product design, validation, and manufacturing. And when I talk about the design and manufacturing of the validation, we are official business partners with Hexagon, VA Grade, and companies like Torre, and for CAD coming to Dassault Systems and Systems. So this is basically our introduction to our team, which is their corporate offices in Bangalore, and we are spread across the country in various cities. And coming to the solution that we offer, coming to the global portfolio of products, right from materials to systems. Okay. So when we talk about systems, it is basically the starting point in the materials section. How we model our materials, how we characterize our materials. Then comes fabrication, then comes part modeling, assembly, and system-related analysis. So when we talk about materials, we have softwares like DigiMat, Material Center, which are mainly used for material characterizations of metallic components or composites and things like that. And whether you are involved in the virtual testing of these materials, where you want to create your own materials, test them virtually, and then analyze them using the FDA tools. We can do it using the DigiMat software. And coming to fabrication is mainly on DigiMat additive or Simulfact additive, or it can be Simulfact forming, which is mainly the fabrication technologies that we have. Then the part related aspects like modeling as well as geometry cleanup and things like that can be done using Apex or Market. Okay. So then as comes to assembly solutions, assembly means comes to the welding or joining technologies, we have again the Simulfact tool for that. Okay. And then system related things. System related things is your FEA analysis, like you can do CFD analysis or structural analysis and so on and so forth. We have SE flow for CFD analysis and NASTRAN, PATRAN for structural analysis, and people might be interested in multi-body dynamics, that is addressed by ADAM software, and also acoustic simulations, which are addressed by ACTAN software. Okay. So these are the various tools that we have. So now, since our point of interest is on Simulfact, that is mainly used for additive manufacturing solutions. So that is our topic for the day. So I will be just giving you an overview of what is Simulfact, and then we will proceed to the specific applications of Simulfact where it can be used for additive manufacturing, whether it can be directed energy deposition techniques or power bed fusion techniques. Okay. So Simulfact basically stands for simulating manufacturing. So simulating manufacturing, or we can say it's a manufacturing division of MSC software. So MSC software is a part of Hexagon company. So they are under they are doing the development for this particular tool. Okay. So Simulfact supports metal-based manufacturing process. It can be welding or any kind of forming analysis or additive manufacturing. And the technology that is being used behind Simulfact is nothing but the mark and the diaphragm solvers. So these solvers are multi-physics solvers which have been there in the market from a long time. And if you take mark, it's a very multi-physics nonlinear implicit code which is mainly working behind the Simulfact to solve our multiphysics problems also. Okay. Then we have diagram solvers also, which can be used in forging simulations or hot forging simulations and things like that, where it is an explicit solver. Okay. So this is an introduction to the SIMUFAC, like how it is there in the picture. So based on the type of analysis or the vertical that we have SIMUFAC forming and SIMUFAC additive and SIMUFAC welding. SIMUFAC forming can solve all the forming related manufacturing processes. It can be in the cold forming domain, hot forging domain, sheet metal forming, ring rolling, and so on and so forth. Whichever is like applicable to your requirement in forming aspects, we can solve it using SIMUFAC forming vertical. And another vertical is SIMUFAC additive. Additive is mainly targeting the powder bed fusion or PGF process. It can be the DMLS process or SLS process or EBM process. Several things can be addressed. Whichever is powder bed fusion techniques can be addressed using SIMUFAC additive. Okay. Then we have the welding. So SIMUFAC welding can address simulations pertaining to arc welding, laser beam welding, and the topic for our today is like metal deposition techniques, which can be all addressed by the SIMUFAC welding model. Okay. So we shall get into that step by step. Like for example, whichever I was mentioning, like for example, if you are doing the powder bed fusion techniques, it can be SLM or selective laser melting, or direct metal laser sintering process like DMLS process, or EBM process, electron beam welding. We can use this SIMUFAC additive software. Okay. And deposition techniques, laser based, arc based, or electron beam based, whether it can be powder or wire based, it can be addressed using SIMUFAC welding software. Okay. The deposition techniques are nothing but our DD techniques, which I was mentioning in the morning sessions. All those things can be solved using SIMUFAC welding model. Okay. So if plastics are involved or composite materials are involved, we have a module called DigiMan, which can solve something like FDM or FF kind of simulation. It can be solved using the DigiMan plastics. Okay. So these are all the modules or different types of tools that we have to solve different kinds of problems. Okay. So coming to our next slide. That is, I will give a brief overview. Yeah. Coming to the next one. So, whenever we are solving or whenever we are performing metal, additive manufacturing solution, or it can be a PDF process or a DD process, there are many challenges that comes into the picture actually. Okay. And those challenges, whether the simulation by doing a virtual simulation can be addressed or not. Or we might be doing in real life applications to arrive at a result. We might do several trial and error using the machine or using the technology, and we go back and then do the rework and things like that using physical prototype or physical testing. So how we can reduce these kind of physical testing, because physical testing anywhere we cannot avoid it. But the number of tests or the number of trials that we do can be addressed by keeping the solution or simulation as a back-end solution actually. So this will reduce our effort as well as your time and effort as well as money which goes into the testing as well as the physical prototyping. So how simulation can be helpful? For example, it can help us in assessing or finding out distortions in part dimensions which is going out of tolerance, or suppose if you are doing a PDF or a powder bed fusion technologies, whether the deformations are coming more, such that if there is collision with your encoder blade and there is a machine jam and then there is a wastage of time as well as material. So these kind of things can be analyzed using the simulation technique, using SIMUFAC additive or welding. And another thing would be residual stress. So all these technologies that are there, whatever is running behind is a FEM FEA or FEA code, finite element analysis code, which will help you to analyze path or path distortion or residual stresses, which are the reasons for part failures, cracks, okay, as well as collisions with the recoater blade in case of powder bed fusions, or it can be delamination in case of DED process. These kind of things can be analyzed with respect to results such as residual stresses or distortions that comes into the picture. And due to these kind of defects, our parts fails in the during the build when you are manufacturing the part, or it can fail after manufacturing part when it is part is performing in the service actually. Okay, these kind of things can happen actually. So how we can overcome these kind of situations is what we are going to study. Then another aspects will be like quality defects and whether the studying or density of the parts, whether the parts are more dense or whether there are some the density of the part is less such that the part is not able to perform in the real life scenario, as well as implications. Implication in the sense whatever we are discussed, like iterative trial and error required, and high cost in time and resources. So these are the reasons why we have to use a simulation. For example, if you see a titanium bicycle frame section, which is manufactured using a powder bed fusion method actually. Okay. So during this method, since this involves localized heating, whenever we are heating a material or a powder with a localized heat source, there are a lot of chances that it will go out of distortion or it can cause crack like this actually. Okay. So these kind of products are manufactured by using support structures here. Whenever we are using the powder fusion methods, we have the part as well as there are support structures. So the support structures are comparatively very less denser compared to the part which we are trying to manufacture. So this can cause some issues like cracking, or it can cause some failure, or you can see the parts going out of tolerances when there is a rapid heating and cooling of the parts which are getting manufactured layer by layer. So these kind of things, how we can address? We can address it up to a certain extent by doing a simulation. Okay. So AM workflow or additive manufacturing workflow to date, something like you have a design with you, okay, and then suppose it might be an automotive or aerospace kind of component which you have designed, and then you want that design to come into manufacturing, and then you want to use it for your application. So what we will do is we will design the component, we will try to build the component actually. Okay, it can be using the SDF or the DED methods. We try to build the components, then we try to inspect the components, like for any failure or any defects in the product actually. So once you have identified defects or something like a part going out of tolerance, we need to repeat this process again. We need to either change your design or modify your building strategy. You have to modify your scanning strategy, or you have to modify your heat input strategy, or heat input parameters you have to modify. So this is something like a very cyclic process. We have to do many trial and error to achieve a successful component which is able to perform in the real life scenario. So this takes a lot of trial and error. So what if we can include something like that? You can say an AM simulation in between the what you call it as in between your design and your build, actual build. We can create an AM simulation, and we can detect these kind of defects in your simulation, in your virtual simulation, such that you can save all these building and inspection, all these things efforts can be reduced. Okay, that is our main idea of doing a simulation. So from this simulation, first, like if you are able to find out these things using a virtual simulation, we can always go back to our CAD design. We can modify the design, or we can modify the build parameters, and then we can analyze it. We can arrive at a particular less can say product, build with less errors, which can be finally send it back to the build, and then we can continue our design or inspection process. So this will reduce our cycle in which we are trying, investing in our trial and error issue or testing or things like that. So there the simulation comes into picture. So this is where we are going to use the simulation as an added or a complementary solution to reduce the efforts in manufacturing. So in simulation, if we talk about, there are several scales by which we can do the simulation actually. Okay. So it depends on the type of simulation that you are doing or the kind of results that you want, or it can be something like the computational effort that you are looking for and things like that. Okay. So here we have three. They have divided this into three main simulation types. One is the macro scale simulation, meso scale simulation, and then we have the micro scale simulation. Okay. So macro scale simulation, when I talk about macro scale simulation, it is nothing but a purely mechanical simulation where we are trying to capture something called inherent strain which comes in the components when the component gets printed. So these inherent strains can be purely mechanical, and it can be material specific, machine specific aspect. Okay, when we are talking about the macro scale. So why we use macro scale is it is very less time consuming process. It can we can easily do experiments to capture the material behavior easily to make your physical print, and as well as it delivers the distortion and stresses. So if our aim is to study the distortion and stresses on the part, we can use the macro level simulation section, which can be easily solved using the additive as well as the welding technologies. So next level of simulation is the meso scale. Meso scale means element layer analysis step by step in a hatching or segment wise. Okay. So this is something like we are capturing thermal, mechanical and thermomechanical coupled aspects in the simulation. So if your aim is to study the thermal aspects in the simulation also, then we can use the meso scale simulation, and it will be able to deliver us thermal history as well as mechanical results like distortion, stresses, strains. All these aspects can be solved using the meso scale method. And one more meso scale, the application of meso scale is most of the PDF process that we solve are solved using the meso scale approach. Because as you know, the PDF process is a very time-consuming process where the powder has to be melted layer by layer using the scanning strategy as well as the slicing software. So each layer will be something like in microns, varying from, it can be from 30 microns to 50 microns of material has to be laid layer by layer, and we have to build the part actually. Okay. So when that is involved, it is very difficult to in a computationally when we talk about the computational effort, it is very difficult to analyze it using the micro scale method. Okay. So that's why we use the meso scale method, which is a faster solution, but at the same time we can study the thermal behavior of your body, and due to the thermal behavior what with the distortion, stresses, as well as the the temperature, the melting behavior of the powder or the material that we are trying to use, we can study it using the meso scale. Then the final thing would be the micro scale. Micro scale is the finest level that we can go as far as the finite element method is concerned, where we are using a moving heat source. So this will exactly capture how your scanning strategy is there on the laser, how whether it is a whatever strategy is there, you can model it capturing the G codes from your robot or from your machine. You can capture it and study the moving heat source. The heat source will move along with the time. So this is a completely thermomechanically, methodologically coupled solution where we can study thermal history and as well as the microstructural details also. Okay. So So mostly this method we won't prefer here because this will take more time to analyze. When we are going for a component level or part level analysis, we mainly use the mesoscale as well as a microscale method. And to make this more, you can say by using the less computational efforts, as well as we have to arrive at a more closer results to our reality. We use many methods to arrive at this solution. So that we will be discussing in the coming slide. So when we talk about the macro scale or the mechanical approach, we generally have different techniques to analyze these kind of components. So whether we if we talk about LBF process or the power bed fusion processes, whenever we take a power bed fusion process machine like EOS machine or something like a manufacturing kind of scenario, so there we'll have different kinds of aspects which we are going to consideration. So there can be laser based parameters that we have to take care. Powder quality, how the powder quality is there, okay, and the machine, whether it is a new machine or whether it is used machine. So all these aspects will cause difference in the part distortions or the behavior how the part when it is printed actually. So when you, for example, if you take a new machine like a EOS machine or a drum machine, and when we start printing the part, we have captured some, let's say, some distortions. So after some time, when we change the powder or when we change the material parameters and when we print it using the same machine, then again the distortions might be varying. Your machine is same, but again the results are different. So how can that be possible? Okay. So that kind of aspects can be related to the quality of the powder, the power input. So after the machine gets more and more used, the efficiency of the machine might be coming down. So due to that, there can be difference in the results actually. So to take care of that, we use something like an approach in smooth-pack additive, that is the powder bed fusion method, where we print physical samples actually. Okay. So each and every time when we are doing a print, we will build physical samples, something like these. These are called the cantilever samples. So they are like standard samples which we try to print it on the machine before we print the actual part. So why do we print these samples is like to understand the behavior of the component or behavior of the material actually. So here in this case it can be a titanium alloy or inconel alloys, or it can be something like a managing steel. So each and every time when we print, we should get the behavior of the material same actually. Okay. So what we do here is we try to capture something called plastic strains, thermal strains, creep strains, or phase transformation strains. So all these strains combined are known as inherent strains. Okay. So inherent strains are specifically, it is very, you can say, a particular material will be having a particular inherent strain. If you take titanium, it will have a particular inherent strain, and if you take something like another material or inconel material, it has a specific inherent strain. So we are trying to capture those strains, and then we are trying to build the component inside the software. We try to build the part in the machine. We try to compare the, you can say, the displacement which is coming in our simulation as which is coming in the part. Okay. So after we do that, what we do is we do something called as a calibration study. We will study whether our simulation is matching with our part build actually. Okay. So there are some techniques in the software to, I can say, calibrate your displacements or your strains which is coming in the simulation and the part, and then we extract the inherent strains from the software. These inherent strains will be put in your actual build part for analyzing the actual component. Okay. So from this, what we are trying to do is in the simulation we can't capture all your machine parameters. There can be n number of parameters when you are actually printing a part or using a particular machine. So how we can reduce all those parameters for our analysis so that we can match our experimental as well as the simulation. That is what we are trying to do here in the calibration procedure. So after you calibrate, you can do the analysis. So analysis, as I said, it can be the meso level, which is the mechanical analysis, or if you want to study the thermal analysis, where you want to capture the thermal behavior of the component layer by layer, we can able to capture it. So what does it enable us to predict? We can predict distortion, stress, which is coming on the part, supports or the base plates, okay, as well as peak temperatures, whether the peak temperatures are in the simulation or in the whether our laser parameters are giving us the right peak temperatures to melt the powder, or the proper fusion of the powder is happening, or the wire is happening. These kind of aspects can be studied using the heat flux and peak temperatures. Likewise, we can use the thermomechanical approach to study the part behavior. So here we have a part which is getting built here. So here we can see the layer by layer. This is a PVF process actually, which is solved using Simfact additive. Okay. So here you can see building the parts. How we can say it works on a technology like activating the element layer technology. So where each and every layer is activated based on the type of input that we have to give here. Okay. So it can be something like, from this analysis we can study the distortion, stress, strain results which can be displaced, and we can study deviation. So most of the parts which are manufactured in using the powder bed fusion technique or the DD techniques, the main challenge is addressing the distortions actually. How we can address the distortions, as we had seen in the earlier talk given by Manjay. So how simulations can be used to reduce these kind of distortions? We can study using the part techniques. And in addition to that, the part might be subjected to something like heat treatment, because initially when you build the part can have residual stresses which are highly responsible for cracks or failure of components during the cycle, whenever during the operating cycles of the part. So heat treatment processes can relieve the stresses. So we have methods to relieve the heat, relieve the stress using heat treatment techniques. Whether it can be something like stress relief heat treatment, or it can be specific heat treatment technologies which we want to simulate, something like a quenching or something like technologies with respect to these temperature over time kind of scenarios. We can simulate it using the Simfact welding as Simfact heat treatment model. So you can see here how the equivalent stress buildup will happen after the part is being printed, and how after the heat treatment is done, how the stresses can be relieved from the part. So it will improve the material characteristics of the component. Okay. So for this we have several creep laws, etc., which can be input into the software. Based on this creep laws, it will calculate the stress relief heat treatment techniques. And then we have support removal. So if you are doing a LPF process, we might be after building the part, we may have to separate the part from the base plate using the cutting or the removal of the support structures from the component edge. So whether that can be simulated or not, yes, it can be simulated using the cutting and removal support structures, where it will essentially, as far as the FEM is concerned, it will change the stiffness of the structure. So whenever the component is attached to the base plate, the result that we get is entirely different when we cut it from the base plate, because the stiffness is released from the component and the end distortions will be completely different when we are doing the component, or when we are manufacturing the component and when we are measuring the distortions with the base plate. So sometimes we use the base plate, we do the heat treatment along with the base plate, and then we take the measurements after cutting. So several methods can impart several differences in the behavior of the component section. So those kind of things can be addressed using the Simfact module section. And then we can also study hot isostatic pressing, HIP process, which are most commonly used in powder-based manufacturing process, where we provide the time as well as the pressure over time data, and we can study the relative density of your build before as well as after doing the densification. Okay. So it uses some densification formulas to arrive at the relative density of your particles. So all these things can be used to optimize your AM process change. So mainly it involves additive manufacturing, or whether we are doing a heat treatment, then we are cutting and removing the base plate, or doing a heat process. Everything can be analyzed virtually in a additive or additive in the simultaneous additive environment. So how it helps is, for example, we have to do these different scenarios in a physical way. For example, let's say we are having a part like this. We have a few support structures which are modeled here, and we are trying to print it actually. Then we find that there are some distortions coming on the part. Okay. So we are trying to let's say we are telling, okay, the support structures are more. We want to optimize the support structures such that we want to get less amount of distortion at that particular part actually. So how we can use this simulation? We can use a simulation to do support structure optimization, to optimize the amount of support structures or the areas in where the support structures are necessary to reduce these kind of defects or these kind of issues which can come in the reliability. So those kind of support structure optimization as well as part optimization can be done using the simultaneous additive tool. So here I chose, for example, distortion as well as stresses which are studied for build, during the build, during the heat treatment, during the cutting, as well as removing the support structures. So and we do the each and every application or each and every process, it will give us the resultant result in a real-time scenario. Despite the best efforts, distortion may be still out of tolerance. So, despite doing all these things, we might still face issues. So, how we can overcome those issues? So, next one would be something like, so you might be facing, you might be hearing something called compensation techniques. So, even if you, I can say, use all your parameters right, and whether you are doing all the scanning strategy or any strategies and the material aspects you have taken care, then also at the end of the print you may get some deviations or we can say distortions at the end of the print. Okay. So this can happen during the physical print. For example, if you see here, this is your initial component which with the initial build and with the initial support section. So after printing, the component will distort, okay, and then it will give us some distorted geometry, which is when you measure it, you will see that the part is going out of the tolerance section. Okay. So what we do is we do a simulation on this, and we do something called as a compensation. We compensate the geometry in such a way that when we print the part, we should get the part within the tolerance section. Okay, so that is known as the distortion compensation. So there are right now in simulation softwares we are having specific methods to address these distortions by using automatic distortion compensation to take care of these kind of errors that these kind of issues that can come in the part builders. Okay. So these are all automatic options are available in the software where we need to do certain number of iterations to arrive at a part which will help us to print with the least distortion. So this shows a snapshot of how the simulation happens in the software and what kind of components that which can be printed using the PPF process. So this is an example for an impeller plate which is printed using the powder fusion technology. Can be something like titanium or infrared kind of materials. So here we can study the distortions. Here we can study the temperature distribution as well as the the effective stresses when you are building the part. And also you can say see the stresses that is getting involved during the different aspects of build. So now we have after build we are doing the cutting operation, and then the support removal will happen. So at the end of we will get the end where we can study the stresses which are coming on the component. So this is coming to a case study. Right? This is the green team wheel carrier case study. So here we have the component. So here this was a study done in collaboration with Renisho and Simulpac, the green team in Germany. So here we have a formula student electric team, University of Stuttgart. So they collaborated and made a study on this particular aspect. So here we have the component here, and it is something like a suspension, upright bearing carrier. So this to get this part printed. So here you can see the component. To print it using the additive manufacturing technology. So whether this would be feasible or not. So if you take an automobile or a vehicle like this, whether the component will survive with respect to the loads which are coming on the vehicle or not, we have to study. That too by using a powder bed fusion technique. So here the material used was TiAl6V4, the titanium powder, and the tool steel was the base plate for this particular material. I mean for this particular build. And it had around 5 lakh elements, and then around 82 layers of elements. And thickness of the support is 0.3 mm. Okay. So these are the inputs that we need as a whenever we are considering FEA perspective. We need to discretize the model and we need to make the necessary element count so that we can study the behavior of the component when we are building the part. So on your screen here you can see the component getting built, and then you can see it is getting built, and then the base plate is removed, the support structure removal is done, and then the further processing is done. So there, after building the part, you can see here the measurement correlations were done, which requires specific predictions actually. So this shows the component, and then there are certain locations where the point 1, 2, 3, you can see several locations where after the building the part or after the building the part in the tool in the software, we are trying to match it with the real life print actually. Okay. So there you can see the scale displacements which is showing in the simulation as well as in the experiment. So we are getting a good amount of correlation between the experiment and the simulation actually. So this was done for different stages, like build stage, then base plate removal stage, support removal stage. So all these things aspects, different studies are done with respect to residual stresses as well as displacements. We can do it. And heat treatment was done to reduce the, of course, the heat treatment has to be done because building any component using the laser-based techniques will involve residual stresses in the component. So how to relieve those things? We have to use a heat treatment cycle to remove the residual stresses. So that is being shown here after explaining how the residual stresses are removed. Then one more aspect is cracks, which can it can be something like a crack which is forming between the support structure and the component. So that can be predicted using the software. We can use it by simulation can predict cracking basically at local locations like these, or it can identify high risk locations and conduct virtual trial to reduce the risk. So after building the print, if you are finding these kind of issues, again you have to go back and then modify your input parameters actually. So that will involve again the cycling process where you have to use the material to build the component as well as the time which is required to build these kind of components. So that can be very much reduced if we are doing a simulation. We are arriving at some study where we can identify such issues well in advance actually. Okay. Then another aspect would be, even if you build a part, like morning we had seen we are doing something like optimization studies to make the components lightweight in nature. Okay, lightweight in the sense like using additive technologies where the conventional part, which is shown something like this, whether it can be optimized with respect to the weight such that we can remove the material from the component, as well as we have to maintain the performance of the component or the strength of the component, which has to perform in a way such that it has to perform in a similar way as the real component or the conventional component. So for that we do the topology optimization studies, where we use the loads and constraints on the component to study the material where and all the material is not required, it can be removed, and then we build the part, we study the part, and then finally we decide whether we can use this particular part for the actual component actually. Okay. So for this several studies can be done. For example, using the topology optimization, we can make multiple design concepts like design variants. Okay. So the topology optimization tool will give you a number of design variants. So in these different variants, if you observe, there are slight variations in the design in each and every design actually. So which is the most apt or which is the most you can say suitable design which you can use? It has to be studied using the virtual manufacturing as well as the further FEA analysis actually. It can be stress analysis or fatigue analysis. Several analysis has to be done to arrive at a solution actually. So that can be done further to the printing or the virtual printing analysis. So in this virtual printing analysis, when we are getting these different variants, which is the best variant we can pick? Some variant might give you like less weight, but it may not be feasible to use that aesthetic wise, or it can be part performance wise. It cannot be used in the real life scenario. So we cannot always judge based on the weight reduction or things like that. We have to consider many other aspects, like we have to do multiple FE analysis, whether it can be static analysis or dynamic analysis we have to perform, and then we need to arrive at a particular design. Okay. So here the topology optimization will help us to optimize the component with respect to the material topology based optimization algorithm. So here it shows we use a tool called Apex Generative Design. There are several tools in the market, and one of them is Apex Generative Design, where we use the initial CAD design and we use the loads, the design constraints, and the loads to arrive at the a design by using the material removal using generative design kind of techniques. So here you can see the component where the material is removed wherever it is necessary, and the material is retained wherever there is a design constraints. It can be both locations, constrained locations, or it can be the component phases where we want to retain. Those parts it will retain, and then it will create a generative design based on that. So this particular, it will give you a smooth geometry which is ready to print actually. So you can send this as an STL file or a CAD file. You can export this file and then feed it into your additive manufacturing simulation to further continue from the continue into the additive manufacturing simulation using the A or the laser based technique. So here it shows the component which is used for the AM build simulation and the cutting process. So here you can see that particular animation shown over here. So after this we study the distortion which is coming on this part. We will see whether this is able to print the part. Sometimes while printing this part will try to fail. Like for example, if the distortions, local distortions are high, the machine will, the recoder or the machine will come into a halt, where if the recoder jam happens at a particular layer, then we have to discard the entire part and then we have to start building the part again. So this physically doing it is a very risky task, so we use the simulation to check whether these kind of issues can happen in the real life scenario or not. Okay. Then we have another aspect is like optimization of build process. Like when we are trying to build a part, we suppose this is a base plate of the machine. sometimes machine comes in different sizes, like it can be 280, like if you take the US machine, it will come up to 400 by 400 mm base plate dimensions. That can be the maximum dimension the machine has. So whether your part can be printed using that kind of setup or not, we can use it using whether we can use a single part or whether we can build multiple parts on the base plate. So if you take a big component like this, the base plate will be we can only build a single component on the base plate actually. And we can study on different aspects like build, you can say what you can do is the orientation actually. So which is the best orientation for building the component. So here if you see, he has kept a different orientation, and here if you see it is a something like a different orientation actually. So in whichever orientation if you print, you will get minimum distortion or minimum failure with respect to the part. So this can be, to do this in a machine, you will have to do, physically build this and again build this and then compare it. Instead of that, we can virtually simulate it and we can study that, which will make us our efforts much lesser. Okay. So that is this particular tool is comes along with the SimFact additive tool, where with respect to different inputs, it can be build height, your orientation. It will generate the best orientation for your model based on different inputs we are trying to give it. So here is the support structure optimization. So when we are talking about PBF process, we have again the support structures which has to be generated along with the part. So if you are trying to print the part, the support structures gets printed along with the part actually. So wherever we need the support structures, or which locations we don't want the support structures, so we can use support structure optimization to reduce or add support structure based on the geometry, based on the loads which are coming on the component actually. So this can be simulated and we can use it for your actual print. So after arriving at this optimized support structures on the part, we can send this part to the actual printing. Okay. So here you have the component is printed and then it is could be used for the particular the way. So this is something like what we are talking about the PBF. So when we talk about the direct energy deposition or the laser based or arc based technique for DD components. So how we can use SimFact welding for that. Okay. So SimFact welding also is a specific tool. So it can solve welding kind of scenarios where we have arc welding, laser based, electron beam based, or you can say direct energy deposition, or any of these several aspects can be simulated. Recently, several years before, since nowadays we are having the additive technologies into pictures. So development started happening in this area, that is the direct energy deposition, and SimFact has introduced this particular direct energy deposition module inside the SimFact welding engine. So why welding is because we use the same techniques to build the components. It can be laser based heat source or the arc based heat sources. Whatever the heat sources, we are using the welding techniques to build the components layer by layer. So that's why it is introduced in the SimFact welding module. So here what we generally do is here everyone must be aware. We build the CAD, then we build the DD path planning using the path planning tool from the machine. We take up the the path scenarios, and then we create the G code and we try to build the part. Okay. So building this part directly, as you know, it is very challenging for arriving at a particular part which is having specific the behavior or with respect to distortion, stresses, or it can be something like the microstructural details. Everything can be an aspect when we are trying to build the component directly. So whether any simulation can come in between this, and whether we can make use of the simulation software to reduce our efforts in these when we are doing metal deposition techniques or metal deposition methods. That is the main criteria. So why do we need a simulation because we are already doing the physical trials. We are already doing that in our day-to-day life. Why do we need a simulation actually? How does it help us? Like, if you are doing the physical printout, you are saying that, like, if you take the design and process of like a confidence on a graph, you can see that we are very uncertain how the things would end up at when we are doing a physical build. Okay, we have to do n number of physical trials to arrive at a simulation or to arrive at a specific output, which can be time consuming, which can be expensive because we have to use a lot of material to use to print these kind of components, and it requires physical parts to be printed, to be physical. We need to do many tryouts to arrive at some solutions, as well as limited design changes. So since we have to print this part each and every time, it will involve a lot of effort actually. So that will limit our design changes, as well as the freedom to choose the design, or whether we have to change something again, we have to do the things again all over again. So this kind of things can be addressed using the simulation. So DED manufacturing is a complex and can be very difficult to predict. So that is why the simulation or such kind of FEA simulation can be used, or it can be complemented along with your physical printing. Mainly because the DED quality can be impacted mainly by the thermal management strategy. Like, for example, if you are using the heat source to melt the component or melt the wire or powder, whether the heat, the laser parameters or these laser speed, scan speed, everything is appropriate or not. Okay, if it is not appropriate, it can cause overheating or underheating, and based on that, it can affect our end result, which can lead to distortions or many manufacturing issues with respect to the quality of the component which is getting produced. So that is why this can be very challenging. It can be impacted by this thermal history, and it can be impacted by residual stresses. We saw in the earlier slides how the residual stresses build up when we build the component actually, as well as base plate deformation. So whenever we are trying to build a component, you must be knowing when we have a substrate or a base plate on which we are trying to build the component actually. And as we build the component, continuously we are heating and cooling. Okay. So this continuous heating and cooling involves a lot of material characteristics which gets changed during the formation, during the part formation, as well as during the base plate deformation. So this involves a lot of if the base plate gets deformed too much, that will also affect the end part productivity. So these kind of things, whether we can address it or not, we can address it using simulation up to a certain extent, where we can use these particular tools to analyze these things. Additional potential issues, like for example, undesirable like microstructure, cracking, and fatigue failure in service. So these can all happens after the component might be built, and when the component tries to perform, it may undergo some failure or fatigue in the service. So all these are potential issues that can be come across when we are doing a DED or a direct energy deposition methods. So this results, what happens is, what we do is, we have these all issues. What we tend to address these issues, we often use physical trials. Excess physical trials, scrap or rework becomes more actual. Okay, many things gets failed, and then you have to again start from scratch one or step one. So that involves a lot of scratch and rework that happens in scenarios in a build service. So virtual tryout. Virtual tryout is something like which is shown here. So here we have the base plate on which the part is getting manufactured. So the heat source can be laser based or wire based, or it can be laser based technique or additive or arc based techniques. We can use either of the techniques to build the component or simulate the parts like this. So from this we predict process outcome like thermal, distortion, stress and strains actually. Okay. and then we understand the outcome before any physical trial. So we try to, for example, if we try to build the part and we measure it using some measurement, we find the part is going out of tolerance. So how do we do that? Like what parameters we can modify to bring the part into tolerance actually? It can be something like a scanning strategy that you are trying to use, or something like a G-code modification that you are trying to make, that can be studied using the DD or the manufacturing, simulating the manufacturing process. So here we can study many things like power settings. For example, the power that goes into the simulation or the printing, clamping or fixing strategy. So wherever you are clamping these components, so how the clamping strategy is there, based on that, the distortions also might vary in the real life. Okay. So then deposition sequences, how we are trying to sequence the deposit using the metal or wire-based technique. Interpass temperature, whether it is using any interpass cooling or heating in between the passes. So that also will matter. Okay. Then purposefully building the parts out of nominal and many other things which we can study. So all these things, if you are doing it on a physical tryout, it will take a lot of effort. We can always use these kind of tools to optimize your settings actually, and then we can build the part. We can compare it with your physical build. We can come at a conclusion whether this is okay or not. Okay. And this particular thing you would have seen in the morning slide. So here we are trying to the repair approach using the DD techniques. So here the process-oriented approach. So we can see the you can say it will support all kinds of criteria, whether it can be something like a deposition, able to handle large models, whether the model is large or whether it is having multi-axis deposition, and we have whether it is using a process-oriented user interface on the shop floor. For these things, what we try to do here is we don't have a limitation as such in terms of the size of components which we can print, or the complexity of the component which we are trying to print here. So this will give us a process-oriented approach. It can be something like supports all DD principles. Whether you are using a laser, arc, EB, wire, or powder, we can use in all types of DD disciplines. And we can use a direct G codes from your machines or your setup. You can directly import it into the simulation, and you can start printing the component. So when I'm showing you a demo of the software, I'll show you how to work on the tool. So this shows an animation where we are having the additive manufacturing distortion simulation where the part is getting printed. So here we can see the heat source which is traveling through the component, and here we have the simulation for that particular tool. So we can see the heat source moving. And there are several methods to model the heat source. Like we can use the moving heat source, or whether we can also use the thermal cycle methods to model the heat source actually. And what all we can study stress, distortions, as well as you can say strains and displacements on the components when we are trying to build it. So this shows for different heights when the part is getting built. So at the end of this things, we can see the stresses which are developing on the part when the part is getting built. So here we have a sample which is getting printed on the base plate. So here we have the convex side and the concave side, and then we have the dimensions on which it is getting printed. So 30 layer with 18 mm of total height is what the dimensions are there, which is mentioned over here. So after printing, we are trying to they have validated this for the deformations which is coming on the component in the experiment as well as the simulation. So this is a comparison study. This is like a research paper is available. If you require, we can share it for your further information actually. And then this shows the simulation on the part which shows the after printing what are the distortions which are coming something like if it is lifting from the base plate, or if it is having something like outward bending deformation is happening when we are trying to build the part actually. So whenever the part is getting built after a certain height, it has started to distort. So this shows a simulation where versus a 3D scan of the component, where we can make a comparison of the deformations, out of plane deformations, which is coming in the simulation as well as the 3D scan component. So we can see a similar kind of behavior. So validation is done for particular square geometry with 3D scan. So here we can see the part getting printed inside the software, and we get the result from here. And we are also actually printing the component on the base plate. We are getting the scanned data, 3D scan from the part. We are comparing the 3D scan with the simulated data. Okay. And then we have this can be done within the simulpact additive, where we have the distortion compensation tool, where we can do a shape comparison between the simulation and scan data. So after doing the simulation, whether your simulation is matching with your real print, real life print, you can make a comparison study. But you can get the scan data, get it as a STL file, you can import it in the simulpact welding software. We can simulate the the part in the simulpact. We can compare the two parts, and we can see how much of deviation is coming between the simulation and the scan data. So ideally, we should be getting a close correlation between the actual build and then the simulation. So here one more thing is for DED, most of the tools where we face the challenges in getting the laser scan path or the scanning path. Okay, that is a very difficult path. Like earlier, FEA codes were defining these paths manually by defining the path, defining the distance, or getting inside the tool, and then according to the coordinate systems, we were trying to define the path in the tool, and then we were trying to import it. So right now the tool is the simulpact can readily import the G code directly into the tool, where it will readily read the laser scan path, and you can see the build directions, the scanning path directions, as well as the strategy, as well as even the input, like power input and things like that. You can directly import it into the tool actually. So we don't have to spend time in these kind of scenarios where we have to define the scanning path in our analysis. So it can readily import the G code, and we can define the layers, and then we can start simulating the problem. Okay, so this will help the users to reduce the time they are spending in pre-processing. Okay. Then transient solution. So as we have the scan paths and the input here directly, we can define our read source. It can be laser based as it is shown here, or it can be an arc based, or the Goldak model which we use generally for the arc weld arc welding thing, or it can be a cylindrical laser beam which is used as a heat source. So we can model this using the simulpact welding, and we can start using it actually. Okay. Then we simulate it actually. So this shows the simulation. It has taken the G codes, and it has taken the heat input parameters from from the inputs as an input, and it will build the component. And another thing would be element set. So each and every layer that you are printing, we have to give a set of elements. Since it is at the end of the day, we have a finite element simulation. So we need to have a certain number of elements at each and every layer of your build actually. Okay. So generally we use the finite element codes to generate the finite element mesh. So here in FX, as hexagon, we are using the FX tool to generate the finite element mesh. We can also use the other meshing tools like Hypermesh, ANSA, many of the popular finite element boards that are there in the market. We can use those to create the mesh, and then we can automatically assign the elements to each and every layer that we are having in the DD repository. Okay. So that can be decided by the user, or software has certain tools to decide in each layer how many layers of element we can take in. That will happen based on the heat input geometry that we are having as well as the parameters that we are having. Okay. According to that, it will automatically take the sets, element sets in your model. And also we don't have to worry about the contact related things, because earlier in normal software or FA codes, we are generating the each layer and we are trying to import it and we are trying to define the you can say the path. So here we can what we can do is we can mesh the entire component as a single component like this. We can mesh the entire component, we can readily import the entire component, and inside the tool itself we can segregate the paths based on our layers based on our requirement. Okay. So here it shows the scanning paths which is taken from the G code. So this is a sufficiently, like for example, this shows a very something like a larger model. In this larger model also we can try to capture the scan strategy, and we are trying to build the component. So they have solved even models with over 2 km of build layers without grouping the layers. G code contains over 80 single linear movements actually. So it is not, the size of your model is not a constraint, but computational efforts can be a constraint. So you may need to have larger machines to solve these huge problems, because FA code at the end of it requires computational efforts to solve these kind of problems. So this shows a nose cone model. I think morning we have seen this similar kind of model. So the simulation happens like this. So here we have the razor blown powder DD. So it took something like a 48 hours of solver time, this particular model. And we are using the, you can say the laser based heat source to, to simulate this particular component. So it has, there are several ways to simulate this. We can use the, if you see the both the animations here, you can identify like how the the animation is there, like how the the heat elements are getting heated up. So here you can see a whole circle is getting heated up, but here you can see a parts of this is getting heated up actually. So this particular thing that we have several simulation techniques. For example, if you have to build this part, it will take a lot of time to simulate this. You see like this 48-hour simulation time. So to reduce this, we have certain methods, like we don't have to use an entire moving heat source. You also have thermal cycle methods, and then this kind of reduction methods where we can readily simulate using simplified techniques to reduce our calculation or solver time actually. So this can be done using the simulation. This is called as ATC method or thermal cycle method, which will reduce the simulation efforts which is there for the components. So next we can see here there is a repair operation actually. So morning we will see how they are using DD for repair. So if we have the model which means we need to be repaired, we can readily bring it and we can define our scan paths. We can see the we can make a thermal study, or we can make a thermomechanical study how the metal deposit which is happening here can impart the bring the considerable deformations or any kind of issues in the part when we are trying to repair the part. So these kind of repair studies also can be addressed using the simulfact welding module, where we can use the DD techniques to do that. So this also can be addressed using simulation. So the next one is for example, here if you see here, fundamental studies for simple geometries. So here you can see a study which is being done for a simple, like you can say a square or something like a rectangular pattern which is built on the base plate. So at the end of the simulation, we can see some high stresses which are there in the base plate. I mean base of the component which is attached to the base plate. So there is high stresses coming there. Also high strains are also coming there. Okay. So whenever this is happening, what we can infer or what we can arrive is like when you build the part in a real scenario, something like this, there can be chances of delamination. So delamination can happen from the base plate with the part. So this can be well addressed. Like for example, before building the part, if you are trying to get this kind of study, you will come to know that okay, this kind of scenario or scanning strategy can cause this kind of stress or maybe delamination in the part. So according to that, you can change your laser parameters or input parameters to avoid these kind of things in the real material. Okay. So this has there is a comparison study with this is with respect to the temperature and the height or the temperature and the thermal cycle. At a particular point, we have captured the temperature, and then it is several cycles are captured here. So it is they have shown that it is correlating with the simulation and the experiment. Okay. May not slight deviations might be there, but at least we can get the behavior in a proper way compared to simulation and experiment. Then another study like a distortion, like for example X distortion, which will come normally in the AD processes. So how we can simulate that using the simulation and how they are correlated for the displacement in the positive X as well as the negative X. If you see the coordinate system here, okay, so this is the positive X and this will be the negative. Okay, so that they have made some comparisons. Next important thing would be your heat source, how we are going to model the heat input and boundary conditions calibrated on a single track. So we can make these kind of studies where we have the after doing the welding, we can take the micrograph, weld micrograph, and we can study the heat source with respect to the weld micrograph as well as the simulation. So this will come as a weld monitor we can extract this data as a weld monitor in the simulation, where this shows the penetration, weld penetration in the simulation, and this shows the weld penetration in the actual component, or can say actual welding. So this will also help us in defining or calibrating our heat source. So at the end of the day, we need to get a part printed in the simulation which is close to our real life printing. So we try to calibrate the heat source with respect to the experiment as well as the simulation in such a way that at the end of the day we are trying to match it closely to our experiment. So this kind of thermal studies or thermal calibration study can be done in the SUMOCA welding software, where we are trying to study the melt pool characteristics or by using the simulation as well as by using the measurements which is coming from the experiments. So advanced thermal cycle is one technique where we can use this method to reduce our simulation time. For example, if you are trying to build a very larger component, mostly in the DED techniques, why DED is used is to build large components which are not possible in the powder bed, the laser-based LBF process actually. Because LBF processes, first of all, it is something like a laser-based, and also it has limitation with respect to the powder and the size of the component by which we can build. Normally, the maximum base plate dimensions of a PBF or you can say powder-based machines will come up to 400 by 400. So beyond that, if we have components, we have to look at using DED approach. So for building the part in DED approach for simulation wise, it is very challenging because of the size of the components. So having a small moving heat source, and we are trying to model this. To run this, it will take a lot of time. So there are some simplification techniques like advanced thermal cycle, where it will simulate your entire, you can say, a larger length of your deposit at a particular time, so that it will reduce the time which is used for simulating the entire component. So this will take much lesser time for you to analyze this. It may not be as I can say accurate as the moving heat source model, but up to, you can say, close relation to your moving heat source, but it will reduce your computational effort. So this shows a comparison of the full transient. Full transient is a moving heat source model, which is exactly simulating your laser-based or arc-based simulation as you are doing it in the you can say DED process. So thermal cycle method, you can always use the thermal cycle method to reduce the computation time. But you can see the heat is the layer that is getting heated up. Here this is a moving heat source method, but here the entire layer is getting heated up. So this will take 40 hours to simulate, but this will take only 4 hours. So that time reduction you can get. Then this is also one more advanced thermal cycle method where they are using increasing the size of the the weld length, so that you can get the results in a lesser amount of time. So if you ask me, this is the most accurate method, but the challenge is to simulate the component. Like it will take more amount of time to simulate it. And another showing the thing. So here we have the real component which we saw earlier. So that is showing the simulation like this. And we have on the other part we are using the advanced thermal cycle method. So we can give different factors to this. If you give 50 and if you take 200, it will solve much faster. But it depends on the time and effort that we need to analyze this. So here there is a DED modeling correlation which is done for a component here. So we have component, and from there we have the component and the base plate. We have the G code which is there here, and definition of the heat source parameters. So if you see here, I am having the here we are having a golden heat source, okay, and then we are using the modeling in Apex. We are importing the component and the base plate in welding. We are importing the G code which we are adding from external source. We are importing, maybe we are defining the heat source parameters, and we are evaluating the result. So here there is a study which this is a field study, and this is the you can see the component which we have in the simulation. So there we are having different locations at which we are trying to extract the thermal history of the component. So the thermal correlations at different positions, position number 2, 6, and 9, which we will see it in the previous slide. So here we have different positions at which we are trying to track the history of the component. So here we can see a time versus temperature graph here. So we have the simulation data as well as the experimental data, which shows the correlation. So again, here we can see the weld micrograph. Okay. So in the weld micrograph, we can see the substrate which is there on which we are depositing the material. Okay. So here, what we do in Sunopac is we try to model this using our CAD tools. We try to exactly model the bead, something like on the substrate. You can deposit your material based on the input that we have. So this shows the simulation. This is a moving heat source simulation, which you can see the material deposit getting activated during the simulation action. Okay. So this can be modeled using the right. So this will end my presentation for the day. So what I do is I will just show you a 15-minute demo on the tool, so that we can see how the tool works actually. Okay. Then we can go into the Q&A. So for this we have the welding software. Simulfact welding is a tool which we use for simulating the DED as well as welding simulation, and we have the additive tool for performing the earlier PBF process that is. So that is the powder bed fusion process. So if I open Simulfact welding, so Simulfact welding software, you can say we can simulate arc-based, laser-based methods as well as the direct energy deposition. Right? So here I am opening the GUI. So when we go into GUI, you can go to the new project actually. Okay. So new project, you can see the name of the project and the folder. When we are trying to save the project, you can use a particular folder to save your project actually. So let me say project 1 and say OK. So this will give me a process type. So process type is nothing but the type of process type that we want to use, like the type of scenario which you want to simulate. It can be general arc welding, laser beam welding, electron beam welding, brazing, and resistance spot welding, direct energy deposition. So these are the several modules which are there in the tool, which can be used for simulation. Okay. So for DED, we have the direct energy deposition module. I will click on it, and I will say how many number of components and boundary conditions which I want to take it into the analysis. Let's say I take one component and then I give OK. Okay. So this will take me inside the tool where I can see an object catalog and a process tree. So object catalog will help us to define the components or the input parameters which we want to use in the software. It can be the geometries which we want to import from the CAD or from my FE analysis or FE tool. The materials which we want to define, the temperature, trajectory, weld parameters, and things like that. Okay. And the process tree, like which are all geometries, materials, whichever I am going to use it in the simulation, we can put it inside the process tree. Okay. So I am going to the geometries. Let me import some geometries. So I am having two mesh files here. Like I have created a mesh file for my deposit as well as the wall deposit actually. Okay. So I will just try to import these two. I can select the unit which I want to import and say OK. So this will bring my finite element model which I have created in the finite element analysis software. It can be any commercial finite element model that we are having. We can generate image and we can import it using the PDF format. Okay. This is my base plate and this is the wall deposit which I am trying to deposit on my base plate. So here you can see that I have already modeled the entire length for my deposit. I need not bring single layer in my analysis actually. Okay. I can model the entire deposit as a FEM modeling using the FEM modeling tool, and I can bring it inside as a wall deposit actually. Then what I do is I will drag and drop into the component, so I can see the component inside my UI. Okay. Then what I do is I can also define the wall deposit. I can drag and drop my wall deposit inside the output. But before that, I have to do certain things in the object catalog. Like I have to define the trajectory and have to define the welding parameters. Okay. Or else it will not allow us to drag and drop it inside the robot. So I will define the material for my analysis. So let me go to the library. So when I go into the library, I can find several database materials which are already available inside the Simulpack editing software, where it will show me the different input parameters required to required for the analysis actually. So here I am having that particular material library. Okay. So for welding, if I take welding, so totally there are a lot of materials available here. So I am taking welding. For example, if I am going for a particular grade inside this, okay, let me say I will just take this particular material. So when I bring the material inside the Simulpack GUI, I double click on the material, I can see the properties of the material. Okay. So mainly what plays in the thermomechanical analysis is the thermal properties, then the mechanical properties, and then the flow curves. So these are all the input data which is required for doing the analysis. Okay. So the thermal properties like thermal conductivity, specific heat capacity, density, all these are the parameters, and these parameters are varying with respect to the temperature, okay, as a input data. So from where you get this data is either we can use the ready-made data whichever is available in this Simulpack database, which is closely matching with your material data, or we can use the data and edit the data here as per our requirement. So if you are having a data as per your study, you can input your own data into the software. Okay. So this goes for thermal conductivity of the material. Similarly, specific heat capacity or any data that you are having, which is varying with respect to the temperature or any parameter, we can either use the same data if it is matching with your real data, or we can modify the data according to your requirement. Okay. Same holds good for mechanical properties as well, like Young's modulus, Poisson's ratio, thermal expansion coefficient. So all these are the necessary data required for performing the analysis. And flow curves is another aspect. So here we have the flow curves generated for different temperatures. This also can be manually fed using the into the tool, or we can use the data which is available in the database. Or if you want to build your materials from scratch, that also can be done. You right click on the material, type new, click on new, and everything will be empty, where you can start defining your material from scratch. Okay. If you want to use, or if you want to start building your own material, you can start creating your parameters. And once you create the material, you can also let's say add it to the library. So that in the future when you are using the same material, you don't have to create the material from scratch. You can readily import it from the library. It will be saved inside your database library. Okay. And once you create the material, let's say this particular material, you can drag and drop the material inside the component. Okay. So let's say I am having this particular material inside the base plate. I will drag and drop inside the base plate actually. Okay. So my robot or the I can say deposit might be a different material, or it might be the same material. It depends on the it depends on the experiment that you are trying to do. If it is a different material, we can create the different material and assign it to the robot. So whatever you assign it to the robot goes to the deposit. Okay. Then we feed in the temperature parameters. Like the temperature parameters is nothing but the convectivity transfer coefficient, that is the environment, the surrounding environment in which you are trying to print or deposit the material. Contact heat transfer coefficient, which is nothing but the conductivity transfer coefficient, and the emission coefficient, nothing but the radiation or the amount of heat that is radiated in the ambient atmosphere, or the media that you are having around the deposition. So those parameters you can define it in the temperature parameters, and you drag and drop it inside the data. Okay, so that data will capture inside the deposit and base plate. Next would be the trajectory. So trajectory will define nothing but the scan data or the scan laser path or the you can say the robot trajectory in which the material will be deposited. So you can create trajectories on your road. Like for example, if you create right click on this and a new weld line, you can create the trajectory based on the inputs that you have, or if you have a CSV data or the coordinates of your trajectory, you can input as a CSV file or an Excel sheet, or we can start feeding your data as per the requirement. For example, I am giving the data here for just to show you. Okay, let's say this much data and minus 35. So this is nothing but we have done a previous. This according to that I agree. I just give OK here. So this will create a trajectory inside the software. Okay. So this I can also take my wall deposit here. In a separate data, I can also you can say measure the data. Okay, I can select the point here like query dialog, or you can use the measurement tool here. You can measure, like for example, which is this point 13, 10, and you can measure the data here. So we can take this data, and using this data also you can create a deposit. Okay, coordinates. Okay, now what I do is, once you have created the trajectory, I will drag and drop inside the robot. So once you drag and drop inside the robot, you can see a trajectory getting highlighted in the screen. Okay, this shows what do you call it? There's an arrow mark here which shows the direction of the path of the laser path actually. Okay, so this can be modified based on the input that we have. And what I do is, I just suppose I have to make modification to the trajectory. I have options like copy and translate. I can position the trajectory. For example, I need something like 0.5 mm from the base plate. Okay, I can position it like this. I can move the trajectory according to the direction that I want. Okay, so let's say I give OK here. So this will get offset by a distance of 0.5 from the base plate. Okay. Then what I want to do is I want to copy and translate the trajectory. So I want to build a specific number of layers above the initial trajectory. So I use a 9 number of layers. I give the thickness, and then I give the direction. So I just give OK. So this will create the trajectories for me above the base plate. So you can see the trajectories are already created once you drag and drop the trajectories in the component. Now what I use, I will just drag and drop the wall deposit inside the robot. Okay, and say all weld lines. So now I have the deposit which is modeled earlier. I want to use this as a this thing actually as a deposit. So you can see the deposit has come. There is a offset distance between the this weld, the trajectory and this one. So you can always use the positioning tools to modify your positions on the component. Something like this. Okay, and you can measure it and you can put it exactly here. Okay, or you can position it based on the requirement. Okay, so this is one procedure how we can do, and another procedure, like for example, here I created the trajectories based on the manual procedure where you went to the trajectory and created it. Okay. Suppose what if I'm having a G code? I don't want to do the trajectories here like this. I want to use the G code and then import the G code and use it as a trajectory. Okay. So I'll just delete all this. So what I can do is I can you can say go to this one, the robot, right click on the robot, import G code. You can import G code or something like APT. Both of these things are supported. I go for the G code and go here. It is supported. The format is .iso file. Okay. When I open that, you can see the G code data inside that. That is the G, NT, that is the feed rate, positioning, all this data from the G code it has taken it here. According to this data, it will create the path actually. Okay, the laser path as well as the input. So once I click here, I just say OK. You can see the code has automatically imported inside the software. So this will readily reduce my time which I use to if I am manually creating the trajectory. So if you have any G code, you can directly import it and use it. And also, the G code also will capture based on the feed rate and the velocity. It will capture the velocity directly into your heat source parameter. So that also will be automatically captured, and it will create a welding heat source parameter here inside the simulation. So rest of the things, like for example, I have created my G code. Okay. Now I will bring in my wall deposit, all well lines. So here you can see in this case the wall deposit is also is also in a similar position. So we don't have to reposition it. Okay. And I just position this G code so that it will properly get aligned to the I can say to the weld deposit. So here I am going inside the robot. Here in the robot, you can see for each weld line, it has created all the parameters. So you can see weld length of 65 and what is your starting weld and ending time based on the you can say scan rate. Just calculated the start and end time for each of the weld line. Then we have the trajectories. In the trajectories, we can like make the modification, like orientation. Can modify the orientation. Right now it is oriented in the Y, so I want to make this oriented in Y, and also I want to give an offset of some values. Okay. So here you can see it will show you a 2D schematic diagram of your torch angle on your this. So how the torch angle is oriented when you are depositing, that it will be shown in a pink marker. So here you can see that here. First weld line, second weld line, third weld line, till the end of it. Okay. So if I am offsetting, like if I give an offset, so here you can see it has taken the offset also. Okay. Now I'll say OK. So here you can see that all the weld trajectory and heat sources model here. So in the heat source, I need to give the power which I need. You can either give your current and voltage where you are trying to weld. You can directly input the electrical parameters, or we can give direct power as well. So power in watts, like let's say if you are giving something like 700 watts, 750 watts, and just for an example. Then what you can do is you can give the efficiency of the laser, mostly 0.6. Okay, and heat source. Heat source. Where what kind of heat source you are trying to use, whether you are using a wire-based or a wire-based method, or whether you are using a laser-based technique to weld your to deposit. You can use the two types of heat source. One is a conventional gold-like double ellipsoid model, or we can use a laser-based model. Okay, for laser. So here I am having the dimensions for my laser, that is the upper radius, lower radius, and the depth. So I can enter based on my experiment. Let's say 1.3, and the depth is around 0.7. And volume heat fraction, you can give it as 1. So there is something like surface heat source and the volume heat source. So if you provide volume heat source, the heat source will be distributed in your entire volume within the laser heat source parameter. Sometimes the heat source can get split into surface heat source also, where some of the based on some experiments people have found that like in surface also there will be some part of energy that will be used by for heating the surface compared in addition to the heating the component or the material inside the laser dimension. So that can also be given. So So right now we have given the body features. It depends on the experiment that we are going to do. We can give accordingly. So once I define that, we can see that the process has become almost complete. For example, if I am missing some parameter in a process, like relating the material, you can see that particular area, it will become red in color, or that particular object will have a red color. So this indicates that something is missing inside the particular input. Some input is missing inside. So what we do is, here it says that sometimes the material we might have forgotten to add the material. So once I add the material, it will become you can see the black in color. Okay. Then before any process, you can do a check, model check. So model check will tell you any issues in the pre-processing. So for example, it says no boundary conditions have been added to the process. So if you are doing a FA user, you will come to know how important is the boundary condition for any analysis. Okay. So boundary condition in the sense that this is a mesh, and this is also a mesh. So this is a deformed body. So in a deformed mesh, we have to have whenever we are doing a thermomechanically coupled analysis or a static analysis, we need to have the boundary conditions actually. Okay. Something which is holding the component, it can be a clamp or a fixture, or it can be a bolted location. Okay. These are all the real boundary conditions. So unless we we simulate the real boundary conditions here, our results might be different compared to the experiment. Okay. So we should take care that we define the boundary conditions as close as the experimental setup that we have. So if there are bolts here which is holding the base plate, we need to constrain the base plate as per the real scenario. Or if you are using any clamping to hold the base plate, similarly we need to model the clamping forces and clamping fixtures accordingly. All those things can be done here. So now let me say, like I am having a boundary condition as a bottom. So here when you right click on this, you can see several new boundary conditions. Okay. Here you can see a bearing. Bearing is something like you can say a table on which this plate might be kept. Okay, that is a bearing. Fixed nodes. Fixed nodes can be something like bolted locations where the plate might be fixed. Clamping might be for the clamps which are used to hold the component by using some certain force. Okay, so I'm using fixed nodes here to fix the component. I'm constraining in all the directions. I'm trying to fix the model. Okay. This can be, I'm just selecting randomly just to show you, but we need to select the exact location where the base plate is getting fixed. Now I fix the base plate actually. Now if I do a check, there is no error of the body. Okay. Now what I can do is, I can over the process parameters, I can study thermal solution or thermomechanical solution. Thermal solution in the sense we don't want to study distortion or stress. We are just doing a thermal study. For example, the heat source study. Heat source study in the sense that whether the heat source is properly penetrating inside the component. As I showed in a previous slide, we need to have a correlation with the red microgram and the real, we can say, the analysis. We need to do a heat source or a calibration study. So this will be much faster than a thermomechanical solution. Okay. Now I'm just giving a OK and I'm trying to run this. Now I'll start the analysis. So now the simulation will get started. So it will start, so we have around, can say 10 load cases here, starting from the first load case to the end weld. So it will start doing the simulation. So this particular simulation, we can see that whatever is happening in the real this thing. Actually, on real time, you can play it and you can see the simulation aspects actually. Okay. So we can study temperature and peak temperature inside this simulation. And other than that, since I'm running a thermal simulation, the other aspects won't be available, like stresses or strains. This is just to study the heat input. Okay. So what I do is I will just stop this for now. I'll just show you a completed model which I have already run it to check the post process. Here I am having a DT division, the same thing, same setup. We have used the input and we are trying to check the results. So here I can see I have run a thermomechanical analysis. Okay. And I have given analysis end time as 2500 seconds. So here our welding time is 54 seconds. Okay. So after welding time, what it has to do? It has to do something like a cooling. So the cooling, interpass cooling or interpass heating, everything can be defined within the weld lines which are shown here using these controls like pause time, like follow time, like lead time. These are different controls that we can use to simulate research. When I see the results, you can see this is a moving heat source kind of simulation that we have here. And you can see the heat source. Okay. So it is following that G code or path that we give as per the input that we have in the model. So this is a thermal output. We can study peak temperature output. The peak temperature output will give you the maximum temperature that the component is going through it. So this will show you a study, like it will show you whether all the material that is there, it has been melted beyond the melting temperature or not. Okay, that will show you as a peak temperature. Temperature value will show you the instantaneous temperature which is happening when we are simulating the part action. Okay. So this we can take it, for example, if you want to know it at a particular area, we can always take some flipping planes to study the behavior. Okay. For example, I will just reverse this. So you can study here what is my heat penetration which is happening on the component action. Okay. So here we can see, we can make measurements of that. For example, measuring the length of the heat source, measure the depth, measuring the depth of this. Or we can, suppose we want to note down the temperature, we can open the query tool and we can note down the temperature gradients here, whatever is there on the different locations, right from the starting line to the bottom or across the line. We can make the graphical plots of the thermal history. Okay, this will collect all the data on all the points and it will show you a thermal history on the component. You can plot all these different results. All these different results can be plotted, like temperature, heat flux, stresses, normal stresses, displacements, distortions. All these different things can be plotted for a particular particle. So any particle we can choose and we can monitor the result. Okay. So let's say I'm having a layer number 1. So I'm just taking a section of this. Okay, I'm having a bottom point here. I'll try to capture that bottom point. I'll have a history. So you can see the thermal history based on time. So here you can find the heating cycles, heating and cooling cycles in between, and after that we have allowed it for cooling. So it will go for the cooling cycle. So we can set the limits also in this. Okay, let's say I want till 500 seconds. So this will give you the data till 500 seconds. Let's say I have the data till 60 seconds. So this will generally create the data for the 50 seconds. 100. So it will create the data accordingly. So this data we can export this. If you want it to be exported as a CSV file, we can export this data. If you want to further use it for your other tools for further analysis, we can use the data from the simulation tool. And further to use this one, we can check displacement, that is a distortion, and we can see the distortion pattern here, how it is coming. So if I keep it in this particular view, we can see the distortion effects here, and stresses which is coming here at this location. It is getting attached to the base plate, that location, as well as other things like if you are studying principal stresses or normal stresses, like say normal Z stress on the plate, on the central area of the plate, you can see that stress is getting generated actually there. Okay, all the studies can be done. I can make a section of this. I can see the data, how it is there. You can capture the points here and you can make a plot also. Like for example, from here to here, to capture the history. If I make a plot, I can get the stress plot. So this will track the history of the results from the points which we have calculated. So first it will give you a kernel history output and path output. Path output will give you the normal stress variation from the ends of the plate to the center of the plate. So these kind of things can be studied. And another aspects would be like something like you want to study weather monitor. You can study the heat penetration, that is the well monitor state. So this will show us something like how the heat input looks like. So the same plot we can see it in a thermal output, or we can study it in the well monitor also. So however we see the temperature complete model. So this will also show the peak temperature. So the peak temperature will give us an idea of how the temperature penetration is going. So this same thing can be studied inside the well monitor. So here it shows very less penetration here. Maybe you have to modify the heat source, or we need to check why the penetration is not happening at this area. So if this happens, maybe there can be chances that component has not melted in that region. Proper lack of fusion mechanism. So these kind of we can make many kind of studies using the tool. This shows a deformation. How the base plate also is deformed. Show only base plate, you can see the base plate deformation. So we can click here, show the minimum and maximum for component. And we can actually show the all bodies. It will show you where the maximum base plate is. So this will be actually studying the distortion resistance. In addition to that, you can keep termination criteria For example, you are depositing one layer, and after that you want to reheat that layer, and you want to cool it down. So those kind of criteria can be defined in the termination criteria. So you are saying that when your temperature reaches 100 degrees, you want to stop the analysis or terminate the cooling step and then continue with the next step. We can do that actually. Okay. Yeah, sure. So this ends my presentation. If you have any queries, we can set it or we can have it later also.
If you have any big queries, you can ask.
Is it possible to preheat the base metal before the burst?
Yes, sir. It's possible. We have a cooling process, cooling and heating process separately. Using that process, you can heat the base plate or copper. And the result will be carried to the next.
So you can include the dwell time before between the layers.
Yeah.
It's possible to include the dwell time.
Yes.
Between each layer.
Yes. Okay. Yes. Yes. Yes, that is the idea. Like, for example, if you are doing a pharmaceutical study, you might be unsure that how to use what is the best scanning strategy, whether it will cause any issues with your brain. That can be, if you do a simulation, you will come to know in prior to printing exam. Then you can modify the strategy. You can start with it. Yes, yes, yes. We can do some iterations, some comparative studies, like we modify, trial and error method we can modify, and we can study like that.
After the deposition, is it possible to study the mechanical properties of the wall? Example, is it possible to study the tensile strength of the wall?
We can study tensile strength, but for that we would prefer to do a multi-phase material, and then either we can create a build, and then we can take those results and we can do a tensile study. But to capture the hardness and all in a correct manner, we may have to add some more material data, like multi-phase, data, like CCT diagrams and DDT. So that will give a phase-wise strength. So if you use a normal material, it may not capture that correctly. We can do, but our results might vary from the realized. We are doing a full test based on the weld strength only, it will give the forces. Right? So if you model the material correctly, we can do the full test. That is possible in 3D.
Can we do phase analysis? Phase analysis.
Phase analysis can be done. But our material data should be having the phase data, either the continuous cooling diagrams or the time temperature diagrams. Normally we work along with GIAN-DED-2700056 software. So if you are having GIAN-DED-2700056 software, you can generate the material, multi-phase material, we can use it directly in system. Multi-phase.
Its output can be taken as input to the.
Yes.
Any other questions?
One of our additional guests of this program, Professor G. Madhusudan Reddy. He was the former director of DML Hyderabad, and he has completed his bachelor's from Kakatiya University and master's and doctoral degree from IIT Roorkee, and he had for a lot of defense laboratories, and he got a prestigious memorial Sudarshan Bharat Memorial Prize from the IIT Madras during 1999, and he has made numerous significant remarks contributions towards the development of critical welding technologies required for the wide spectrum of the defense hardware during his entire career. and is recognized as an outstanding contribution towards the welding metallurgy, and has been awarded prestigious Metallurgy of the Year award in 2007, and he has also been awarded the Scientist of the Year of the award in 2013 by the DRDO, and he has also won the Technology Leadership Award in 2018 from the DRDO, and in recognition to his innovation and outstanding work in the field of materials joining and surface technologies. He has been awarded the prestigious Sri Mokshagundam Vishwesvaraya Award in 2018 by Government of Telangana. And also he is now heading the additional chief professor at NIT Warangal, as well as is the chairman of BrahMos. Now I welcome you onto the dais, sir. Thank you, ready, sir. And another one of our additional professor is Professor Venugopal. He is also a scientist at DMRL, and he is also a chief professor at NIT Warangal. He is also an expert in the structural integrity, and he has done a lot of interesting works in defense laboratories, especially with respect to the metal forming. I welcome you also, sir. Thank you. And also I will welcome Professor David Borel onto the dais, sir. Yeah. Now I request Dr. Madhusudan Reddy sir to give some few overview of his thoughts on the IT manufacturing, and then now we'll move on to the interactive session about how we can able to address the future directions and what is the future knowledge with respect to the IT manufacturing in the Indian scenario, and as well as from the Professor David from the US, and what is the standard and qualification with respect to the applications orientation of the IT manufacturing possible. I welcome you, sir.
So, good evening to all of you. Thank you, Dr. Manjay, for the nice introduction, and I'm thankful for you for the invitation for this interaction and meeting. And I looked at what you have studied in the last 3 days, on additive manufacturing. Okay, you in fact have covered, Professor has covered various additive manufacturing processes and service properties of using, especially for TD, and how to repair and how to retain the original functionality of the component, metallurgical aspects and numerical simulation, and how to control the inflow and so on. And I looked at, there are a lot of case studies. He has covered it, and so one thing is we're looking at repair and manufacturing. They're looking for damaged components, bring back the functionality to as original, okay? But at the same time, we're looking for cost effectiveness. So for that, because we're looking for focused thermal energy sources, earlier we used to do by using welding technique. In fact, additive manufacturing is nothing but welding under complex boundary conditions, severe constraints. The bead size is big, not everything very small and finer. You're using wide additive manufacturing process, you're using powder-based. What is the reason is the melting and solidifying, and it's nothing but welding. But there is a lot of differences because the effect of cooling rates are so high, and the structure is so fine, and there's no time for the element to segregate, because generally in welding, there's a melting, there is solidification, then during the solidification, there is segregation of the elements. Have a lot of problems and the way you're going down. But here, everything is so fast, the segregation is almost minimized, cooling rates are extremely fast, you're getting a fine structure. So that is the beauty of additive manufacturing. And because since you're using the fine focused energy, so you're able to repair it precisely and effectively. But I wanted to say a few more things because what are the trends in alloy development right now happening in additive manufacturing, so that I will say a few lines, then you can ask any queries. So as of now, we are trying to use the existing alloys. We are not trying to develop a new alloys. I think we should move to new alloy developments. And we are all, as of now, we are using a metallurgically simple alloys we are using. Very simple alloys. Aluminum silicon we are using is the simplest alloy. But you're not looking for the complex alloys. Because that is metallurgically more complex. And understanding the phases is quite difficult. So you have to thorough if you're putting physical metallurgical aspects there. That's the reason most people are not working on a complex alloy systems for additive manufacturing today. And we are looking for whichever is alloy is weldable, that is printable. Whichever is printable, you can go for additive manufacturing. So whichever alloy is not weldable is you cannot make it. So that's the reason we are looking at the silicon alloy, which is EJs. Everybody's keep on working on that. But you're not looking for which is aluminum alloys, which is having high strength and it is difficult to make it. I have a lot of problems when you're depositing, okay, you have a certification defects. You have a lot of problems. And understanding and behavior, getting the properties is highly difficult. I don't see any alloys, right now aluminum alloys, they are using aluminum scandium magnesium alloys, which is non-heatable, and aluminum silicon alloys plus aluminum magnesium alloys. And to some extent people are using aluminum copper-based alloys, but we're not able to use it. So we should look for aluminum alloy, which is the high strength alloys, and we should be able to make weldable, okay? And how to look for the weldability. And the moment you understand the weldability of the material, then you can be able to make powders, and the powders you can use it to make products. And you're not looking for you're using a simple post-weld, post-deposited heat treatment, simple treatments, but you're not able to build the complex. Whatever you are applicable for wrought alloys, you're making the powder and you're producing the components, and you're not able to get required properties because it's a complex heat treatments. One has to look for that. And right now, the most focus is on dimensional accuracy. Shall I get a good bead, good surface roughness? You're always looking on the dimensional accuracy. That is important for repair and manufacturing. Not all about that. But when we can look for structures which is having good properties and how to make that? The big question mark. And always are looking one process for all materials is impossible. That we use depending upon the application, depending upon the requirements, we have to choose a problem. In case of DEDs, okay, I'm looking for that, it's good for repair, okay, and good for certain kind of combinations, but in all, not all. I want to make a huge structures, you cannot make huge structures by using DED techniques. You have to go for wide additive manufacturing process. And if you want to go for magnesium alloys and to produce the component, it's not possible using the powder because the powder is more of aggressive nature. So you have to look for wide base. So it's not possible. So then how to look for that? Okay, that's the question mark. Second thing is when you look for when I said whichever is alloy is printable, is weldable. Okay, how many people are trying to work on the material? Till today, the most of the materials, advanced materials, what we have developed and used it, we are not able to manufacture the components because of inherent problems. Look at aluminum zinc magnesium alloy. To weld that, we are trying to use aluminum silicon based alloys or aluminum magnesium based. Strength is quite low. Aluminum zinc magnesium is quite high. So most of the properties of the wrought alloys, when you are trying to weld it or trying to manufacture anything, we are not able to get the full potential. Most of the people are not able to understand the physical, metallurgical aspect of the materials. Without understanding the material behavior, we are trying to work on making components and so on. So metallurgy is a part of that. Mechanical metallurgy is one of the most important things. It is not a subject at all. A component is failed. You can look at in terms of design. You can look at in terms of the forces, stresses. You can design in terms of look at in terms of microstructures. That is mechanical metallurgy. It is not wedded to only metallurgical people. It is actually a subject to be studied by an engineer who is dealing with the manufacturing and materials. So now the question is how to, we are talking about the repair, okay? We are trying to repair for aeronautical components. The success is, I can say partial success. I want to repair a direction certified blades, which is used in turbines, gas turbines. So I can be able to deposit, and it also is deposited by TIG welding process or any other process related. Now, additive manufacturers come, but still I'm not able to get the structure what I wanted. It should be a direction certified blades. The texture should be in line, difficult to make it. So, for example, you're looking for a cast irons, okay? Big cast irons, okay? You want to repair it. Yes, this is the best process, additive manufacturing process using DD, a huge component. When normal one you would want to repair a cast iron of a huge components, bigger in size, you have to preheat it, then you have to weld it. Here, using DD technique because the localized one, okay, density is so high and you can be able to make it and use that. And most of the forged blocks are trying to use this technique effectively. And sometimes everybody says, okay, additive manufacturing can do everything for us. No, it's not possible, okay? It's not at all possible. For example, I'm talking titanium alloys, there's a structure called equiax alpha. You have a laminar structure, you have a bimodal structure. Equiax is meant for such an application. Laminar structure is meant for something. Bimodal is a mixture of equiax and laminar. That kind of structure you cannot make in additive manufacturing as of today. Because it requires some kind of thermomechanical processing. The moment you make it, you have to deform it at certain things, then only you can be able to form the kind of structure. Impossible. So everything is not possible, okay? And a lot of issues when you make a bead and simple welding, two components, okay, trying to weld, and with one weld we are having so many defects, pores, okay, and a lot of qualification standards we have to establish before putting out on a board, okay, on aeronautical applications. Today, additive manufacturing, thousands of thousands, lakhs and lakhs of layers, okay. If any layer, some problem is that it's not possible to repair it. So you have to develop numerical simulations accordingly. You have to control the molten pool width and depth. You have to make it. For example, okay, you're trying to make a manufactured product, one layer, okay, you keep on putting layers, okay. Then you retransfer, and the first layer is different, middle is different, top is different. The mode of certification, metal is melted and certified. First fellow will certify very fast, you make a cellular structure, and second one is you have a dendritic one, and you have equiax, all kind of things are there in one or two grades. You have to control the heat flow properly. So you have to quantify the heat flow directions every layer, and you have to give it to the machine and to control the process parameters. Without understanding the certification, without understanding certification microstructures, a lot of activities going on in the field of additive manufacturing across the world. So that means you have to go back to the methodology and understand what is the mode of certification. Is it cellular? I want cellular structure all the time. That's the point. Another beauty is you are not able to utilize the potential of the process. Potentially. But without understanding, suppose for example we are facing a lot of difficulties in a gas turbine. The central one is disk should have equiax microstructure. I'm talking with respect to titanium alloys. You have blades, the blade should have a direction certified coarse grains. Sometimes I don't have any grain, it's called single crystals. I'm trying to join these number of blades to disc by using a mechanical fastening. So there are a lot of issues. So why can't you go for welding? Okay, we are trying to weld it by linear friction welding rod. But this process, you can do it locally. What kind of structure you want it, you can create it. You can create a localized your own structures. If somewhere you want it coarse, somewhere you want fine, coarse and fine, you can do that. So you can tell your microstructures whatever you like it. That's only possible to understand the phenomenon of solidification. Then you can create wonders. That's the beauty of the process. So we have to use the process where functionality is difficult by a conventional process. At the same time, can you able to get in a cost-effective way? That's what. That's what we have to look for that. Today, if you want to take additive manufacturing to the next level, at a higher level, I should have powders. And today you are talking powders of very high-end powders. I am working on CM247 alloys, super alloys. I am working on titanium alloys. I am working on internal alloys. People keep on working on that. Try to work on the steels. A normal steel, okay? Use it in normal applications, okay? Then goes. They are not doing that. Most of the powders are not available. Who has to make the powders? Talking about, okay, titanium alloys, if you take 1 kg, maybe 5,000 rupees as a wrought alloy. If you buy a powder, it's by 25 to 30,000 rupees. And the powders is not at uniform sizes. Some were coarse, some were fine, and you're trying to do it, you have a lot of coarse powders. And a lot of wastages are there in that. So how to make the powders which is cost effective way? I don't think in country people are working in an isolated way. If I should be able to make powder with a cost less than about 2,000 rupees, I feel like put it. But there are methods are there are things are there to work on that. But something is not able to do that. There are a number of, in fact, I delivered a talk some time ago here, but this is not the right platform because I came here to repair and I have to remanufacture it. So we are trying to see how to retain the functionality, okay? And so there are a lot of superalloys which people are trying to work it. We don't have powders having a high volume fraction of gamma double prime or gamma prime kind of powders are not existing. One has to work on that. So that we will be named as the first in the world or first in the country to work on that. That is missing. Nickel-based alloys, okay, good amount of materials are available, which is of solid strengthened materials. But we look for high gamma prime alloys, then only we can be able to use the effective use of this particular process. Aluminum alloy, as I said, not more than aluminum silicon and aluminum magnesium. We have to work on aluminum zinc magnesium alloy, in which I'm thankful to and grateful to Professor Manjay. In fact, he took a project from ISRO. He's trying to look for aluminum zinc magnesium alloys, which is high strength alloys. And there is an issue in that. He's trying to modify the composition by adding zirconium into that and some amount of scandium and zirconium in combination. And he's made the powders and is trying to work on that. So that is a good addition, I can say, and he has published good number of papers. In fact, it's very good in that. So when you look at stainless steel, okay, I said marathon steel, tool steels, and low alloy steels which are available, but there are many things which should go for print-ready materials. Materials are printable. From printable to print-ready, you have to take it. That means you have to qualify the process, qualify the techniques, qualify the powder, standard everything, then that alloy is print-ready. I may say printable, but it's not print-ready for me. So which are the alloys which are print-ready for us? They are printable, but not printed-ready. The moment you make, you have a lot of defects. Fusion defect, lack of fusion, pores. Where will the porosity is coming? Because most of the powders are not spherical, they're irregular thing. Your flow head is different. You're trying to control a fine contours. You want a good surface finish. If the powders are not uniform, if the powders are not uniform structure like spherical, all kind of things are there. You cannot control with only scan speed. So long. So that's what my previous well-wisher and former director of IGCAR used to say, that if you're trying to work on anything on welding, okay, it is a total engineering, because you're trying to look at what are the materials given, you're spoiling, you're melting and again you're redoing. The fellow is rolled it, made it, and everything is given to you to make a component. What you're trying to do is you're putting and you're trying to weld it. You've destroyed everything. destroyed everything. And again you have to retain the properties. That means you should be more knowledge, both material and the process condition. Same thing with additive manufacturing. It's a total engineering. You have to, right from it to control quality. People never used to worry about quality and how to make things. As an engineer, my duty is only machine, I am machining. My duty is only to weld it, I am welding. It is a quality man to come and say. But this particular process, we should do everything on time, right on the place itself. You have to control the quality, you have to look at everything. So as an engineer, you should know all kind of things. Then only you can understand. But how many people are trying to do that? And I want a simple ferric stainless steel powder form. If it is there, I can use it for some applications. Powders are not there. Who will make for me? And everybody talking about high end. So let us look at the low end first. High end, okay, people are there to work on high end. So some people should give importance to low end applications so that it will go for cost effectiveness. And if you ever look at working on sucralloys, working on work on materials which is commonly used so that you can reduce the cost effectiveness, then you can implement it. That is missing in that. For example, look at duplex stainless steel powders are available. Duplex means what? It is a mixture of arsenic and ferrite. 50% arsenic, 50% ferrite. You have a arsenic stainless steel, 100% arsenic. You have a martensitic stainless steel, 100% martensite. Duplex is a mixture of both ferrite and then arsenic. But when you melt, what happens? The mixing will not be there. So it may become slightly more arsenic, less ferrite. You will not get the properties. Then you keep on controlling the parameters, looking at the big dimensional control, very nice, and other things. Internally, the phase is phased out. It is not 50-50. So unless you don't understand physical metallurgy of the duplex stainless steel, how to add the powder, how to control the cooling rates, so that I'll get the good combination of microstructure without any difference. I want to say one more thing before opening to the dais to the questions. One of my colleagues is keep on doing research in the field of titanium alloys. I'm talking the 1990s and so on. He's getting porosity. Porosity is because when you're melting, okay, metal is molten condition, the gases will be soluble in more. When it is solidified, the solubility of the gas at the room temperature is less. So high temperature is more. So when you are melting, okay, because the temperature is more amount of hydrogen is gone, more amount of oxygen is gone, and it's okay. When cooling it so fast, no time the gas will come on. It will come as a pores. People said, okay, you go for electron welding, it's completely under vacuum, okay, you're doing. But they also are getting pores. So that's the kind of research. So they keep on doing research over the years and publishing papers. Ultimately, there's no answer at all. Go back to intermediate and find out Sievert's law. The partial solubility under vacuum under root of P. So your partial pressure is going down. So what are the materials you are putting that one which is there in room temperature and you are putting inside in the vacuum, and because the partial pressure has come down, the gas is coming within that itself and forming pores here. So what we learn? A basic we are learning, we are living at the basic itself. You have to apply the basics when to use it. I learned ABCD 26. I also know, but I cannot write a poem. I cannot write a proper letter. Doesn't mean that I know all. But I should use the basic of Darcy 26 letters and I should be able to implement properly. Same way, basic engineering, if you have to understand well, then the qualification, standard things, anything is okay, fine. At manufacturing, I said, it is nothing but welding in one way. You are qualifying and requalifying standards, so on. That's slightly bigger in things. When it comes smaller, you have more challenges in that. How to do that? I hope, I think, I can talk any amount, any number of hours I can talk. If you give time to that, okay, I'm having a number of slides, but this is not the time to think. I came here only for interaction, okay? If I have any questions, okay, I can answer. Otherwise, there are people who are having a lot of experience in the field of additive manufacturing, they can answer. That's what I told to them. And Professor is there, and my colleague Dr. Venu is there. He is a structural integrity person. How the porosity will fail, okay? It will have catastrophic failure, okay? So it's good. With the combination of mechanical and if you understand the mechanical metallurgy, I think anywhere you go, I think you can face any engineer, any part, small or big. Only two books one has to read, whether a mechanical engineer or metallurgical engineering. Only mechanical metallurgy if you read is enough. I think you can answer anyone anywhere in the country you want. That's more than enough. But that takes to read that and to understand the simple book, okay? It takes years, it takes entire life. That's all, okay? Thank you. So, any questions?
Yeah, thank you, sir. Audience, any queries from your side if you would like to interact with
now we are more knowledgeable because last 3 days and notes you are reading and other things, so you are more knowledgeable and professor is much more knowledgeable. So we have to, so you can, we can only give suggestions, sir. We cannot answer it, okay? So now please.
Yeah.
Good evening, sir.
Yeah.
Sir, is particle size distribution matters in additive manufacturing by doing deposition, integrity, and other additive manufacturing process? Particle size.
Particle size, it depends on the functionality. It should be very fine and should be spherical in nature for the flow variety. So that is a quantitative subject term, okay? But it should be fine in micron size and spherical. It should not have any internal pores and other things. Should be particle means particle. Internal, if you look at particle, there is another pores are there in that. Okay? So that kind of thing, it will not, when you are welding, if the particle itself is having pores, then you have a defect while depositing inside. So power density, particle density, and size and distribution, it's standards are there.
So
it should be spherical.
As you said about the spherical, so it should be uniform or non-uniform?
It's uniform.
Uniform.
If non-uniform, what happens is fine particles will melt, big particles will not melt. By the time your scan speed is so high, you end up lack of fusion there. So fine. And should not have any kind of internal pores or gas. And particle, some particles are hygroscopic in nature. The moment you open, it will absorb the, for magnesium, you take it. It's hygroscopic in nature. So more, I think you have to go back to polymetry. You don't understand that one. So when everything is ready, only you play with your only process parameters. That is a toy. With a toy, you can just very unidirectional, multidirectional, cross directional, get the properties. That is the one way of work. Otherwise, you understand this. So, but the number of standards depends on the material to material.
Okay, thank you, sir.
Good evening, Professor.
Yeah.
After your briefing, we are feeling something different about our research.
No. I'm not telling you that.
No.
I'm telling you the things, okay, what will we do with that?
You have changed the direction of the research.
Yeah, thank you.
Because when we think of and discuss with the ETNs, when I started research in the beginning, they used to say people are only searching for the advanced and not able to go to, but look at the down, what is the fundamentals. When some ideas address me, talk about the basics, fundamentals, what is, we don't think about how the engine works, try to understand what are the components of the engines first, how many bolts are there, what are the sizes of the bolt required, systems required. So we are pleased to listen to your briefing for sure. So I gave some basic some curiosity.
Okay.
What is the scope of this 3D printers or additive manufacturing in India?
Scope wise is scope, and right now we are trying to use for static applications. I'm talking about the defense industry, okay? And until today, I think we never get any component, though we are making for dynamic applications, which are the fatigue and fan and creep and other things. Because we don't know how many defects are there and how it's going to behave. That kind of database is not existing. I don't think any papers are there is talking about fatigue properties in total. And so we have a lot of uncertainties are there. But no doubt we are trying to use it for static conditions, which is even fails no problem at all. But classroom components we are not using. And where some duct is there, where some kind of valve is there, we're trying to use it. But recently we've gone for the engine valves also, okay? We're trying to do that, some of the fineness in that. Why we're looking is, we want to have internal contours, okay? It's difficult to machine it, okay? So this is the only process, so we're trying to use it, okay, it's meeting the requirements, okay? So slowly we have to come up to new things, because we thought of a number of layers and you are measuring when last piece you are looking, every layer you are not looking properly, then something is there and we don't know, okay, how to repair it. Uncertainty is a lot. But for example, one of engine, which is a scramjet engine, and it's an ramjet or scramjet, okay, we have to use internal cooling inside, okay. Internal cooling means same fuel will go, because when combustion is going on, the temperature inside is 3000 degrees centigrade, and outer temperature should be only 100, and the entire heat should be either by you absorb it by way of coating or extract the heat. So cooling conformity channels were close to that, very fine channels. Okay. That is only possible by manufacturing, nothing else. We are using that. Okay. So it's going on. We are developing day by day. So, but only thing is, at the end, if something goes wrong, it will come back to zero. For example, recently one of the space program things, that's internal thing, automatic product is broken into pieces. So then it means the issues are there in that. But over a period of time, I think we'll come back.
A couple of slides from Sir Goral presented a couple of days. So you have seen some of the parts larger parts manufactured by So all the other participants also may join me in listening from you. What is the role of this additive manufacturing in DMR or ISRO? What type of larger equipments you have? How much you have?
Large means okay, because one need to look at the cost effectiveness one. Second thing is really required to make when I am able to do with a normal conventional process, why should I go for additive manufacturing? Why should I go for that? So you have to look for the criticality. Conventional is not possible, and you have to reduce the weight, reduce the cost, and that kind of things. Okay, not that I can make ship. Why should I make ship? Okay.
So was there any? This is for simple.
We are looking only for small components.
Yeah, small components. Yeah.
Where internal machining is difficult, internal brewing is difficult, and at the same time we are trying to reduce the weight. 1 gram weight also is important for us. We are, by using that, instead of using conventional things, okay, I am wasting a lot of material. One, let me waste, no problem at all. But internally, I am not effectively design my component accordingly. Here I can design to suit my applications. Whereas earlier I am designing, looking at the manufacturing into consideration. When I design whether manufacturing fellow can machine it or not. But today, forget about manufacturing. Can I design it? The moment you design it, you can produce it. So I am able to get a lot of benefit. But the benefit comes over a period of time. And no one will put, even if I develop new material, if I were to go to the actual application, sir, it is taken nearly 10 to 15 years. Sir. The reason is just to be qualified at various levels. So materials will not go into the aeronautical applications. Sir. You may do a wonderful job, okay, but it has to be certified a lot. Certification, qualifications, and reactivity, all the things. It takes years. Sir. So any aeronautical thing, could you see right now, okay, so much welding technology is established. Look at aeroplanes, all are riveted material today. Why is not welded? There are uncertainties are there. And riveted is much better. Even crack comes when it goes stop on another riveter. Crack ends there itself. So what kind of design I wanted, okay? What can you design around it? It's varies. So we have to wisely use the technology. So by using additive manufacturing, it means a conventional thing is rolled out. No, that is the space will be there. Any advanced technology means a basic engineering is no, basic engineering is required. But unfortunate thing is many people don't read how to read drawings, how to draw it. So drawing is zero, engineering language is not there. So that's all. But we have to learn. Drawing is the future.
The aim is for primarily for the prototype making. Is there a chance, or because of its cost effectiveness and performance?
But for that's what I said. Dynamic applications, fatigue and other things, it fails. So how to qualify? Somebody says it's good, then only you put it to the next level. There itself I am having a lot of difficulties. So my machines has to be controlled in such a way that the meltable shape, if I fix it, I have to keep on changing the meltable shape. Here it is okay, next time I have to try to increase it. The moment I say you should be able to go back to the actual machine, then accordingly control the parameters. So that kind of sensitive machines are required. So it's all only engineering of your sensors and other things.
The surface finish of the components produced out of the CM differs with the process power. Is there any specific finishing process required or implemented?
After AM products, there are post operations are many. If the component is you are able to do machining and some kind of a buffing and other things, fine. If it's not possible, some internal channels are doing. There is no possibility for me to do. There I should get the surface finish. What the designer says I should get it. See, my channel size is only 0.5 by 0.5. 0.5. So when doing that, then powder particle is start, I cannot prepare it. So for IIT Hyderabad, they given a major program to make confirm the channels of 1 mm by 1 mm. They gave it to us. When you're looking in water, okay, just say we're walking to the other side. No, it's not going. So internally when you bring the particles, when you do DED, so some of the particles is stuck into that. How to repair that? Not possible. So that means so we're not able to make a good surface finish. So the project we have to close it. We have to close it. And another way we have to do it. Not looking at that. People say no, DED can do everything, you get fine surface finish, everything fine. But somewhere the powder is not melted, it has blocked the channel. You cannot have a drilling machine to drill 1 meter length, such a fine drill. And the channel is not straight, it's a zigzag channels. This process cannot meet my requirements. People may say openly, okay, I can do wonders, okay, but in practically there are a lot of issues right now we are facing. Where give me a program for that? They said they can do it. No, sir, with the DED we cannot do it, with the powder base we will do it. Powder base today depends on your channel size, then it has to be welded. Another one, I want 4 meter length. I don't have such a big thing. So if I build that one, I don't know, can I put that much effort of money and energy on that? So let us look at what we can do with existing materials, how to move further, how to get to your effectiveness, then think about it. But the direction is multi-directionally we are working. Maybe it's okay, sometimes good, sometimes not good.
So just for some little understanding, the defects are corrected using a DED process. Is there a limitation of the defects like the surface defects or root defects that can be?
Yeah, some defects. As I know the standards, okay, the porosity is there, there is fine pore, if it is not interconnected, if it is there, thought about thickness, is there off thickness of that material, number of pores are there, yes, it is good. Because it is shown. But pores are clustered in there, it's a problem. It's a problem. Sometimes, okay, very fine pores, we are not able to detect it. But without defects, nothing is there in the world, okay? Everyone, every person, every material, there is a defect is there. How much defects are able to tolerate it? It's a design based on that. So, 100% defect. Even if defects are there, you can heal it, okay, by heating and other things, so many things. But you cannot have 100%. You are not detecting, but I am having defect. You are not detecting, you don't have an equipment to detect my defectness. See, using UTS, ultrasonic, okay, using X-ray, or 20 micron size, you can able to see that. Below 20 micron size? No. Till today, no. So you are thinking that 20 microns is a crack which is already there. Okay, if it goes to 20 microns to 30 microns, 50 microns, by using fracture mechanics approach, this is okay. This is fixed crack length. With this, I can able to work using fracture mechanics segment. That's. But below 20 microns, you are not detecting. If plenty of cracks are there at 20 microns nearby there, you are not detecting. We don't know when it will fail. So fail analysis, let it fail, you analyze it, understand it, then you implement it. So existing components, over a period of so many years, we understood, okay, how it is behaving. This is the manufacturing products, okay, another 10-20 years, you may get all kind of things. But at this stage, with some kind of uncertainty, we have to move. We have to move, okay. We have to take bare enough. But we look at where it's not possible by conventional methods. So it's not. You want to produce number. No, you cannot produce number. You want to produce dye with the dye and quench, they keep on dyeing. That can you go for additive manufacturing? Take a plate and punch it and get number of components. Why are you looking for additive manufacturing for that? Not required. So look at your functionality. Look at your functionality.
Sir, finally,
yeah.
I don't know whether it's appropriate to ask here.
You're open.
Yeah. Looking at our works of our ancestors, building the lakes, temples, mindful sculptures, without any simulation, repeatedly I have done minute works.
Simulated, you don't know. They are able to read, they are able to visualize it. Today we are not able to visualize the third dimensions of a given product. They say, what is third dimensions? Can you do it? If I give 2 dimensions, third dimension they cannot understand because they never put that. Our concept we are not thinking. So drawing we are not teaching, okay? First year is Indian drawing not required. That is not required, this is not required, so core subjects are not required, everything is only advanced is required. But gold again it requires ABCD is only 26. So when we are going to teach that, so it is required. That's what recently when I reviewed IIT Madras and Mathematical department, I said core subjects you have to give it, other subject is remote. Because they have given opportunity for us to write our own comments, written comments. Yes. You can remember, those subjects are essential. Someone said, employer said, why are you not taking my people for your job? He said very clearly, so he's an US employer, he said very clearly, sir, I can teach my domain expertise to the people. I have to fabricate this, what is required, I can give a training, but fundamental I cannot teach. Fundamental you learn from your basics. Difficult for me to do that. I don't have that much energy to teach. But I have to manufacture this thing, I will teach, I will train you in 1 month or 2 months how to bring this. That's all. Fundamentals, I cannot teach you. Fundamentals you learn. So fundamentals we are not learning, we are only learning this. Domain knowledge you are learning, but not fundamental knowledge. That is things you are missing. Anyway, this is not the course for the BTech people, okay? I'm sorry.
I think this is the final question. To my knowledge, IITs are for some mission buildings. If by any chance, any IITs or any industries or anybody, maybe based on Make in India, is there any attempt to develop, build 3D metal printers in India?
People are doing 3D printers, many are there. They're doing. See, the question is, if you ask us for design, you can design it. People are there. If something is available in 1 rupee, I am doing it, takes 2 rupees, you are going 1 rupee there. What I can do? It takes 2 rupees for me.
That's one
possible.
BFW. It's also made by India.
And that's the reason government has brought a new rule that somebody is designing the machines here, if it's costly also, please buy from here on. So we are not doing all. When I want to buy a machine, a 3D printer for something else, put a clause there. Isn't the country anybody is doing? Why there is doing? You have to buy, it will cost is double also to buy from there only. So government is all kind of this thing. No problem.
I think there is an attempt between WARC and IITs to develop hard disks. Instead of importing from China, some hard disks are getting developed.
Disk means what? I think disk means only.
Hard disk for computers. Hard disk for computers.
I don't know. I have no. I don't know much about that.
Thank you, sir. Thank you very much for your.
Professor, they are not asking questions of you because they understood very well actually.
No, you're doing great. Yeah, keep at it.
Because I'm the first one, they're attacking me, not you actually.
Of course.
So good.
So there are some set of few questions.
Yeah, fine.
Ask.
Yeah, fine. You framed it or somebody has given to you?
Like, especially the repair application, is it an excellent technology compared with the welding in the laser powder bed, the DED process?
Definitely, much excellent because your density is so fine and very high density, precise you can make it, control the damage very well. I'll leave it to the professor, we can able to because he's having vast experience in that place. So please.
Sure. Yeah, I mean, yeah, the repair, the aspects of repair, is first of all, as you mentioned, is we have to be dealing with high value parts, certainly to begin with, for to make, really to justify the repair. You know, we'll be looking tomorrow with case studies for repair. So I think that, it's a very important aspect, and I think it's, as we'll see, the technologies that we deal with, particularly the DED, are going to be extremely well suited for doing repair.
Okay, thank you. Another question, like what is the current state of qualification and certification of GIAN parts in US with respect to the application?
Yeah, you're talking about qualification? Yeah, it's an area that is one of my soft spots, so I can't really talk about the state of qualification, since that's really not an area I work with closely. I can tell you that maybe the doctor can talk about how what qualification is. This is really sort of an industrial concern. But I know that it is an extremely important aspect of doing business with particularly working again. I mean, I'm sure you will agree, working with defense, it's vitally important to qualify and to verify the parts coming out. How it's developed over the years, I can't really say. But other than to say that I know that it's been a very hot topic for some time. So I go to the conferences, I see there's always sessions running on qualification of parts. And it's a very complicated aspect of additive manufacturing in general. And there are many different approaches too that also make it very complicated. So unfortunately, I can't talk about the development or the evolution of qualification, other than simply to say that I know that it's a critical aspect of what we do.
Okay. Yeah. Thank you. Another question is like GIAN parts, how good they are in terms of damage tolerance? Can promise the damage tolerance designs when you consider for the applications?
Yeah, we're talking about, so to make sure I understand, we're talking about the damage tolerance of the parts.
Yes.
In service.
Yeah. Yes, in service.
In parts of service. Yeah, I mean, it obviously is again, that's also an important aspect. To make sure that the parts can perform successfully in service the way they need to perform. That's largely determined by the design and by the materials. So as is always the case as a materials guy, I leave the responsibility on the designers. Of course, the designers lay the responsibility back on the materials people. But it's, you know, to develop the damage tolerance, certainly additive is in a position to be able to have a lot of flexibility to be able to adjust the various parameters in the process of the feedstock and the additive process itself to be able to do that. And the materials people are working on it, the designers are working on it, and to some degree, what I've seen over the years is with the technology and the community on damage tolerance is really coming to a better understanding of what additive manufacturing really is and what it can do and what it can't do. And so the designers, instead of expecting that it will do everything and that everything performs well, I think there's a more reasonable and logical and conservative approach to design to make parts that will really perform the way that they're designed to do, and which of course is that success is will foster and grow the application space because the parts will do what they're designed to do.
Thank you.
There is a connection question here. Some time ago there was a news that I think Pratt & Whitney recalled some of the components in their engines, like worldwide. Those which are manufactured during a particular time using the powder metallurgy technique, they suspected some contamination in the powder which was going into the components. So they thought some microcracks could be generated in those parts, although they may not be safety threatening. And there was an element of doubt, and I understand it led to some even bankruptcy of some of the airlines because they had to. It was led to a serious downtime of the engines. So that recall of the engines and return may take up to 1 year, something like 300 days, which, as you understand, is a large time in the airline industry. Actually, in this context, it was an interesting news how this powder contamination can lead to bankruptcy of the airline industry. So in this context, I would like to know what kind of statistical repeatability will be there in the quality of these parts, especially in emerging design. Of course, we have dealt at length on this, but what kind of statistical repeatability is there that leads to the other question which Professor Mandaya was asking. Are there well-developed test protocols for non-destructive evaluation of these parts? So, any comments on this?
Sure. Yeah. Thanks. Yeah. We are additive manufacturing parts going into service is a very new thing. Because when you consider that the very beginning of additive manufacturing, not its widespread application, but the sale of the very first machine was only about 40 years ago. So we don't really have much of a track record in terms of parts and service. So I've sort of been, I've always gritting my teeth and hoping that when parts, when components and systems fail, that's not due to an additive part. But of course, it's inevitable that this will happen. We took the lessons we can learn from that. And again, this is more of a corporate thing than an academic thing. But my observation is that the current way that, at least in the U.S., for the one area that I'm familiar with is with nylon parts for aircraft. For these parts, and again, it's not like a Pratt & Whitney application because these are not structural parts. But the way that they're qualified, the way that the fabricators try to guarantee that it will perform and not fail is they're doing it on the front side by doing mechanical characterization during the build, and they've established minimums that they must meet before the part will go in service. And it's the test coupons, they can be built in the chamber along with the part. so that which is the best they can do to make sure that what they're testing is what actually is reflective of the part itself. And so these kinds of things that are really what I've seen in terms of how they try to guarantee that these kinds of things don't happen. And certainly, I guess with any manufacturing process, we have, we have a bad scenario like this that unfortunately can have a dramatic impact on the people that are involved. So, so I know it's going to happen, but I'm hoping that it doesn't. With that,
Thank you.
I think a few questions that mentioned to me. It's a lot of work which we are interested to work on smart structures. I want smart ship. I want smart submarine ship. So submarine, okay. How to make this smart house? Smart house means what? You have to put sensors inside the material. Okay. That is only possible by embedded electronics. And then I had to do it by ultrasonic laminations, then go for further. And that day we are doing a lot of work. So everything should be smart. Any sensors are not kept outside, built inside. So that is activity with additive manufacturing, doing a lot using the ultrasonic additive manufacturing process. They are doing a lot. And the questions another one is you can improve the yield strength, you can improve different materials, reduce the density. If you want to reduce further, okay, I don't want material the same thickness everywhere. I want somewhere hollow, somewhere different structure, somewhere honeycomb structure. So you can get the stiffness accordingly. You can reduce the weight and improve your elastic modulus in a better way by using modular structures. That is not possible by any other methods. So we are trying to, suppose if you look at aeronautical blade, okay, turbine blade, it's not shaped one end to other in the same thickness. Internally, you have a lot of modular structure, okay, that gives enough good elasticity, and modulus, and density is low, it's very high. So we have to look for where additive manufacturing can give more functionality and design a product accordingly, meet your further requirement, high temperature requirements, or low density and so on. Then you will definitely get it. Don't look for too big components, too small components. So look for embedded structures and how to make embedded structures. Make everything smarter. Nothing is visible. But all our sensors are there. So the scope of additive manufacturing in India. In fact, recently, last year, the government of India is asked to work on a conference on additive manufacturing itself. And in fact, we had a meeting at Hyderabad and participated by invitation. Okay, we have a number of lectures chosen by a special committee, and government want that. Okay, they want to promote additive manufacturing. We have given a big roadmap for the country, another 10 years, 20 years, where the demand is the country. I think those things I can able to circulate to you because now it's coming in an open thing, which has by Indian National Academy of Engineering started this event. Roadmap we made it, and so industry has talked about that. I think that I can share it, but a lot of good scope is additive manufacturing. Is it possible for additive manufacturing for a mass manufacturing? But this is not a mass. I mean, one by one only we can make it. It's not a mass production or anything at all. But it's look for a specified components, critical designs and other things. It's not possible either way. What is the suggested program for DED? What is ministry? DED is again, it's additive manufacturing in that is coming roadmap. We are looking for design our own programs and multiple programs to minimize the weight and to increase structural strength. The program for DED is not a program for entire additive manufacturing. It's a roadmap is there for the government. I can able to share to Manjaya if it is open by which we only wrote recently. Otherwise, I can able to tell the content of that by not giving the name of that. Okay? But I can quote that because that is open. Okay? Types of defects that can be arrived using DAD. Body the pores, okay, lack of fusion, porosity is a major thing actually. How to control it? You control the way whatever is possible. Otherwise, the best way is that once the product is made, you can go for hard isostatic pressing route. You put the component inside. It will, because of hydrostatic pressure, okay, the defects will be healed. The new technique, okay. AM products are supposed to undergo heating. They know that putting into that kind of things to do. So there are many ways to control the defects. You have to control the process parameters, the way you do it, powders you have to look for that, and process, powders, scan speed, so many things. Okay? So it is routine activities, but we should can you detect that? Okay, once the layer is over, next layer is coming, should you detect then should you repair also. That kind of sensors people are working. Right now you are depositing, making an entire thing, and then you are evaluating. But in situ we should do it. For that from now we should do a lot of chemical analysis, and then we have to have good sensors for that and good feedback control systems. I think new equipments are coming in that way. And then we are depositing, and defect is there, what to do? Okay, throw it and use one new thing. There also defect is coming, okay, we are not able to go for next level. So they would repair of the A product in situ before putting next layer. Then only it's applicable for that. Is there any plan for India to develop and manufacture 3D metal printer? Yes, many companies have done. And the first person is IIT Mumbai, Professor Karunakaran. He has started. In fact, they have given 2 projects on top building. This thing still is doing. I think he is the right person. Okay, he is helping many industries, and he is the first person to do the things. Design a machine for our own programs. And he's really worked for the last 50 years. Now he's able to see the window. It just got open now. Okay, he's able to see the output of that. I think that's all the questions what you asked.
Thank you. Any other queries from participants? Feel free to ask directly.
Sir?
Yeah, please.
I have a question, sir. When we are doing functionally graded materials, so we have to use 2 different powders.
Yeah.
So 2 different hoppers. So, 2 different hoppers will release the powder in different percentage. For example, metal A 20%, metal B 80%.
Okay.
So together they will be released to nozzle. So we'll use one carrier gas.
Yes.
And I just want to know how it will get mixed and then deposited, sir. Because 80 plus 20, when it deposits, what is the procedure? How it gets mixed up? Whether it will be equally mixed like 80 plus 20 together, 2 metals will be.
The powder is getting controlled, no? From the one hopper and another hopper coming to nozzle, then only it's going to the melting stage. No?
But they have to mix now, sir. 80
no,
plus.
It's internally because okay, it's there is a rotating this it's getting like a mechanical mixing is happening. Okay? It's coming, okay, it's getting mixed, then only it's going to the nozzle, then only it's getting melted, then it's going to that portion. Before that one, both are added, then the rotation is going on inside and the mixing is going on. Then we'll go to the next level, then only it comes out from the nozzle also.
Yes, sir.
Then there is a arc.
My doubt is, sir, will it be completely mixed, sir?
The completely mixed means okay, there is a mechanical mixing only is happening, okay? It's like how we have ball milling you are doing, similar kind of things. So there is a uniformity is fairly achieved right now. That's fairly achieved. Why only 2 powders? They were trying to do 3 powders, 4 powders, okay? And one is working is quite complex. I want titanium, I want stainless steel, okay? Both powders are not compatible. Not compatible. So how to do that? How to do that? So what are the problems are there already there, okay? Years have passed, okay, now 70 years has come, okay, for the country. Now what are the problems is 70 years back, now the problem is same. With that. So basic understanding, when 2 people don't know each other, we repair the 3rd man, okay? The problem still exists. So same thing in we are using 2 powders, we want some other powder, okay? In fact, I want to add it, why can't we add it? It into the solubility of this fellow, that put this fellow. This person what is in between, he should absorb both, but he should not dictate his terms. He should be, and those people only should be able to move. And third one who is coming in, he should only try these two people and he should sign it. But most of the people who are coming in between, he is dominated. In actual scenario, if you see in the nature, the two people are not going, third man comes, he dictates the things. Other people are only users. I don't want the other two people are important for me, not a third man. Same thing, what observe close in nature, everything additive manufacturing is we are very close to the nature. Very close to the nature. So observe the nature, what is happening. How nature is, flower is coming. It's coming layer by layer is getting deposited. Can you manufacture the flower? Not possible. So it is coming and is layer by layer and is open and is showing to you. That is the additive manufacturing layer by layer. So additive manufacturing is very, very close to the nature. So you observe the nature. Every technology is in the nature, okay? We are not inventing anything at all, okay? Observe closely, observe their behavior. Materials also same behavior, okay? Titanium, stainless steel don't go each other. Titanium to aluminum, no possibility. No possibility. But we want both to be tied in. Impossible. Impossible. And third man, we are trying to do it. And what are the profits that we are enjoying? Yeah. I will tell one example, I think I'll close it. There is a huge internal pipeline of titanium pipeline. There is another stainless steel pipeline. The pipeline carries almost pressure about 240 pressure, okay? Megapascals, okay? 240. Such a high pressure, okay? You have to join it, okay? That means you have to join titanium to aluminum. Titanium, aluminum, there is no solubility. It forms intermetallics. Whatever technique you use it, to weld it, it's okay. But you bend it, fails. But we need that kind of things. We have to. How to do that? The question mark. So every manufacturer will give an answer to me. Okay, so titanium slowly add 20-30% mentioned, make it to SF and you do it. But somewhere you are adding it form intermetallics. When titanium is coming to SF powder, it form intermetallics. You are adding titanium powder slowly decreasing, stainless steel keep on increasing, you have functional graded in between. But those people are able to move well. But these people are not able to move well, titanium and aluminum. How to do that? Observe closely what is happening. Plumber, what he does when he comes to your house, the pipeline leakage is there. It opens the things and the thread is there, leak is there, put the Teflon tape and put it here. Job is done, okay, leak is stopped. But I am looking for submarine, okay, 20-30 years. When the pipeline is laid at such high pressure, then I cannot put Teflon tape there, okay. That is only for the atmospheric pressure. So can I use the same logic? Can I use the same logic for my components? What plumber is doing? So one question is, okay, you put an internal thread, you put an external thread. This is a titanium, that is a SS. SS to SS we weld it, no problem at all. Titanium welded. Here is an internal external thread. Thread to there is a gap is there. Plumber is putting the gap, filling the gap because of Teflon tape. Can I fill the gap using metallic sealing with metal? The simple one particle is there, you cannot tighten it properly. If the thread is some particles are there, you cannot tighten it. So how can you put metallic sealing in that? The question is, this is the technology. Technologies cost in crores, hundreds of crores. A simple technology. That's why I said, go for fundamental understanding. Brazing is what? Brazing is by capillary action. How the mercury is going? By capillary action. So now I put internal thread, put everything here, put a filler on the top, which is low melting filler, put in the furnace, the metal will melt. By capillary action it goes inside, fill every thread. That's what the green solution is working. All the submarines are working today because of it. That is simple. What is the cost of things? Nothing. And today we are trying to do additive manufacturing. I can make it, sir. With additive manufacturing, I use a gradation, the functional graded. Impossible, impossible. You tell today, ask him, okay, whenever a problem, you do it. We know very well we cannot do it. Okay, you are trying to do it, take something, okay, something will come. So we have given number of programs. I asked ISRO also, right now with the CMD Midani, why don't you get a kind of program with a few lakhs? Anyone can do it or not? No, since they said they won't do it. I gave it a set, but is it possible? Why can't you give the funding? Or okay, you give suggestions. So you can tomorrow come and look, I will introduce to you, okay? So that's the thing. No, see that we are able to do that. That is the only true job today, which we did it. So understand nature. That's all I can say. Thank you.
Thank you, sir. Thank you very much for Professor Malson Reddy and as well as Dr. David Boyle and as well as Professor Venugopal for joining this interactive session. No, you are actually Professor Genetic Particles. Yeah, thank you for the participants. We'll end this today's session. We'll meet back tomorrow in the same seminar complex. Morning 2 sessions and afternoon we'll wind up the workshop. Thank you very much.
Photograph I want to the professor. Thank you.